Unmute your mic.
A very pleasant morning to one and all present here. I'm profusely elated to take this opportunity to welcome you all to the two-day international workshop on nanomaterials for clean energy and space astronomy 2022, conducted by the Department of Physics, Ethiraj College for Women in association with the Indian Science Congress Association, Chennai chapter. 63 years ago, the conceptual foundation of nanotechnology began with the talk titled "There's Plenty of Space at the Bottom," held at an annual meeting of the American Physical Society at Caltech by Sir Richard Feynman. Here we are in the year 2022 talking about those tiny machines which fascinated Sir Richard Feynman. The pandemic is no longer an hindrance to have you here amongst us. We hope that this workshop rekindles your comprehension of nanomaterials and its versatility. The staff and students of the Department of Physics, Ethiraj College for Women, are honored to have you all here. Let us begin the program with the blessings of the Lord Almighty. I request Ms. Ganavashini from 3rd BSc Physics to render the invocation song.
Shri Mahaganapati-ravatu Mam. Shri Mahaganapati-ravatu Mam. Siddhi-vinayako Matanga-mukha Shri Mahaganapati-ravatu Mam. Siddhi-vinayako Matanga-mukha Shri Mahaganapati-ravatu Mam. Kama-janaka-vidindra Sannota Kama-janaka-vidindra Sannota Kamala Layatata-nivaso Komaladara Pallava-vadadara Shri Komaladara Pallava-vadadara Guru-guhagraja Shivatmaja Suparna Kashana-vigna Tatvo Padambujo Gauravarna Avasanadaro Palachandro Naravivinota Lambodaro Uvalaya Swabhishana Pashangushamotaka Prakashakaro Bhava Jaladinavo Mula Prakriti Swabhava Kushadaro Ravi Sahasra Sannipateho Kavijananuta Mushikavaho Avanata Devadasa Muho Avinasha Kaivalyakeho Pamadi Mirigamatanu Gujam Nisari Kitata Nisajanuta Nisari Mataganam Magamata Kita Papa Madimita Mapani Dimitari Panisari Kukuda Kumapanita Kitajam Rigamarisa Nisari Nisari Sakukuda Kupani Pasadimitari Rigamarisa Jamtarita Sani Pamata Dingina Tum Shri Maha Ganapati-ravatu Mam. Siddhi-vinayako Matanga-mukha Shri Maha Ganapati-ravatu Mam.
Thank you, Ganavashini. Now, I would like to invite Dr. Mrs. E.V. Joni Virgila, Head, Department of Physics, Ethiraj College for Women, to deliver the welcome address.
Success can come to you by courageous devotion to the tasks lying in front of you, said our Nobel laureate, Sir C.V. Raman. Very pleasant morning to the intellectual gathering. On behalf of the staff and students, aided and self-supporting, I deem it a great privilege to welcome you all to the two-day online international workshop on nanomaterials for clean energy and space astronomy, organized by the Department of Physics and the Astronomy Club of Ethiraj College, the first of its kind for the club and for the department in the nature of an international workshop, in addition to two international conferences hosted in the past 5 years. At this special moment, as we gradually cherish the blessings of our founder, Sri V.L. Ethiraj, I extend a warm welcome to our chairperson, Dr. Chandradevi Tanikachalam, through S. Sridharan, Financial Trustee, esteemed members of board, Principal Dr. S. Kodai, Vice Principal Aided, Dr. T.B. Usharani, and Vice Principal Self-Supporting, Dr. T. Usha Priya. Pleasant greetings and cordial welcome to Dr. C. Muttamil Selvan, Executive Member, Indian Science Congress Association, ISCA, Chennai Chapter, and Vice Chancellor, SRM Institute of Science and Technology. Dr. S.V. Kasmir Raja, Convener, ISCA, Chennai. Dr. Alagari Swami, Treasurer, ISCA, Faculty of Engineering and Technology, Department of Nanoscience and Nanotechnology, SRM University. Dr. M.G. Raghunathan, Executive Member, Indian Science Congress Association and Principal, Guru Nanak College, Chennai. I welcome 8 reputed invited speakers and academicians from across the globe. Our first keynote speaker of the international workshop, Professor Mohan Raja from the University of Ulsan, South Korea. Professor Jayant Murthy, Senior Professor, Indian Institute of Astrophysics. A very warm welcome to all our former professors of the department, professors and heads of various departments, Controller of Examinations, Deans, non-teaching faculty, friends and well-wishers of the department, students, research scholars, and dear participants from various parts of the country and across the world. The Department for Physics has evolved in leaps and bounds over the period of time, with its inception in 1948 from offering BSc degree program to the student community since 1978 to a research department in 2017. Many thanks to the sincere efforts of our former professors, the great encouragement of the managements in the past, principals and vice principals at all times. The main objective of the department is to encourage students to pursue higher studies leading to research in physics, benefiting the society as a whole. In this context, the department organizes every year various activities for college and school students, like seminars, conferences, workshops, quiz, exhibition, etc., in commemoration of the National Science Day in the month of February, recalling the discovery of Raman effect in 1930. The Indian Science Congress Association, under the auspices of the Department of Science and Technology, Ministry of Science and Technology, Government of India, aims to advance and promote the cause of science in the country. The association with this premier scientific organization in our country gives us immense pride and joy as we foster similar objectives in the service of the student body. Many thanks to our first women chairperson of Ethiraj College Trust, Dr. Chandra Devi Tanikachalam, and the vice principal, Dr. D.B. Usha Rani Madam, for the extensive support and encouragement in making this dream come true. At this juncture, we thankfully cherish the commendable efforts of Dr. Alagari Swami, Treasurer ISKA, Faculty of Engineering and Technology, Department of Nanoscience and Nanotechnology, SRM University, and Dr. S.V. Tesni Raja, Convener ISKA, Chennai, in extending their unstinting support by all means, intellectually and financially, towards this venture. The Astronomy Club, affiliated to Vigyan Prasar, network of science clubs WITNET, under the auspices of the department, caters to the astronomical interests of the student community and has dedicated sessions in this international workshop, attracting students with astronomical inclinations. Many thanks to Thiru S. Soundarajan Perumal, Joint Director, Tamil Nadu Science and Technology Center, Chennai, India, for all the valuable suggestions and great support rendered towards the progress of the club. We hope that this two-day online international workshop on nanomaterials for clean energy and space astronomy, with a variety of reputed speakers from across the world, USA, UK, Taiwan, South Korea, Czech Republic, and India, will nurture the scientific temper amongst all of us virtually connected this morning, anticipating to culminate two broad fields of nanomaterials and space astronomy. I take this opportunity to thank all the speakers profusely for accepting our invitation and for consenting to deliver the invited talk. Indeed, it is a great honor and blessing for the department to have distinguished speakers who have excelled in their own fields of research. I wish that this international workshop would align towards the theme of National Science Day celebrations this year, towards integrated approach in science and technology for a sustainable future, benefiting more than 920 registered participants in this online international workshop. Once again, I extend a warm, cordial welcome to one and all gathered here for this intellectual sharing and discussion. Thank you.
Thank you, ma'am. Now, to present the overview of the IWNC essay, I invite Dr. Mrs. S. Mahalakshmi, Assistant Professor, Department of Physics, aided.
A very good morning. It gives me a colossal pleasure to extend my warm greetings to our Madam Chairperson, Madam Principal, Madam Vice Principal, and our associating professional body, Indian Science Congress, Chennai chapter, under the auspices of Department of Science and Technology, Ministry of Science and Technology, Government of India. We are very grateful to the tandem academicians, scholars, students attending this online two-day international workshop on nanomaterials for clean energy and space astronomy, organized by Department of Physics, Ethiraj College for Women. Despite this overarching caution in COVID-19 curfews, the lure remains for the harnessing nanomaterials for clean energy and to take on the challenges of space astronomy in the blasting free from Earth intact. This monumental event features lots of opportunities to network with partners from the entire world in an exciting environment whilst in translational research and applications to make innovative and upgraded strategic alliances to secure our environment to be absolutely clean. From the nano to macro, we seek to understand the origin of the universe, the ultimate structure of the universe, and the fundamental laws that govern the physical world as the trinity of the next step generation. So this workshop will focus on nanomaterials that may provide new solutions to pressing environmental problems, especially those associated with energy storage application, 2D materials for energy harvesting and storage, electrochemical energy storage nexus. The specific sessions focused on the cutting edge of multimodal imaging technologies, taking a futuristic look at photonic nanomaterials for new directions in the field of informed research and engage our community. Nanomaterials for clean energy has been a tremendous forum to foster cross-disciplinary and intense scientific discussions involving leaders across the scientific fields. So, with potentials to revolutionize the space travel, nanotechnology has the capability to push the human race to the outer reaches of our galaxy and hopefully one day to other stars. It will inspire the generations of explorers and dreamers to challenge themselves and advance the human race into the next era. So now, here we have a cosmic cocktail of radiation exposure of sessions in space astronomy, formation of young low mass stars to chill out in the outer space. I sincerely hope that this two-day international workshop will quench the thirst of nanomaterials for clean energy and space astronomy. Thank you. Thank you for your participation and support.
Thank you, ma'am. Now I invite Dr. Mrs. B. Uma, Assistant Professor, Department of Physics, AIDED, to present the overview of our distinguished speakers of the IWNCSA 2022.
Good morning. I take great privilege in introducing the speakers of IWNCESA 2022. At the outset, I would like to share with you that the department has conducted many seminars and conferences in the past for the benefit of the students. An international conference, CFAS, on cosmology and frontiers in applied astrosciences was organized in the year 2017. Since then, this is the first online workshop. The past 5 years of period, invited talks were regimented in the various topics like cosmology, low temperature physics, black holes and wormholes, nanophysics, age current, trends and future aspects, weather forecasting, medical physics, insight into eclipses, network of researchers on the chemical evolution of life, mysteries of cosmos, green energy system, time management strategies in the evolution of an integral personality, touring on nanoworld, cosmology, particle physics and dark matter, tools and techniques of nanotechnology, and so on. The talks were fruitful to our UG, PG students and our research scholars to modify their self-dom and competency in the various fields. In endurance to it, this 2 days online workshop on nanomaterials for clean energy and space astronomy, IWN CESA 2022, is organized where we have eminent speakers from the diverse habitat. The keynote forum of the workshop consists of 2 keynote speeches in day 1 and 2 plenary talks. The first keynote speech will be delivered by Professor Mohan Raja, Research Professor from the University of Ulsan, South Korea. Subsequently, the first plenary talk will be given by Ms. Bhavna Lalshank, National Central University, Taiwan. Post-lunch session starts with the second keynote speech by Professor Satish Krishnamurthy, Chair of Energy Technology, School of Engineering and Innovation, Open University, Peterborough, United Kingdom. At the end of day 1, we have the next plenary talk given by Dr. Samuel Paul David, Hyles Center, Institute of Physics of Czech Academy of Sciences, Czech Republic. The second day, 23rd February, of this international workshop will start with the third plenary talk by Dr. Ramya Rajaraman, research professional and clinical collaboration, Hoffman Estates, Illinois, United States. Ensuing keynote talk by Dr. Bibin John, scientist, Energy Systems Development Division, Vikram Sarabhai Space Center, Thiruvananthapuram, Kerala, India. A conclusive devoted session on space astronomy will be given by Senior Professor Jayant Murthy, followed by Dr. Krisvan Karthik from the Indian Institute of Astrophysics, Bangalore, India. I sincerely hope that these 2 days of international workshop will quench the thirst of nanomaterials for clean energy and space astronomy. Thank you.
Thank you, ma'am. Now, I warmly invite Dr. Tirumati Chandradevi Tanikachilam, ma'am, Chairperson, Ethiraj College Trust, to felicitate the event.
Very good morning to every one of you. At the outset, I wish to congratulate the head as well as other faculty members and students of the physics department for organizing this great seminar. Online and especially along with the Chennai chapter of Indian Science Congress Association. My special compliments to both the entities for having chosen a topic of very much a socially relevant one, and it is something which is very much needed as far as our energy revolution is concerned. Though I am not a scientist to speak about this particular topic, as a social activist, I am fully aware of what's going around, or to a large extent, I am aware of what is going around due to the effect of human caused global warming and the debate that goes on also about the climate justice between developed and non-developed countries. But these are issues to be dealt with politically by the governments. But scientists all over the world have got a very, very important role to ensure that whatever the serious problem that we are facing now, a solution has to be arrived as early as possible. The effects of change, of the climate change, are no longer it is not an issue for a distant future, as it was thought some years back. It is already very much happening, and the growth rate of increased climate change is not only assessed by the scientific community of the world, but even our farmers living in remote villages are able to perceive it. People like me, who are above 60s, 70s, and 80s, the problem may still look a little bit theoretical. But our students who are in 20s, this problem is more real. They have a vital role to play to protect the globe from human-caused global warming. All they need is the solution they need from the scientific community is that they need to lead a very productive life, a comfortable life, but without using fossil fuel. And that is where the role of the scientists all over the world, how to find solutions which is economically viable for all the entire mankind to switch over from what is now right now is happening. It is very important for the youngsters to find a solution for this. It is for their sake, for their children's sake, and for their grandchildren, and for the rest of their future community, future mankind. Looking at the participating faculties from abroad and from our own country, I have least doubt it's going to be a fabulous interaction of scientific minds that could kindle innovative thinking of our young minds, who are going to be the torch bearers for future actions, whatever need to be taken. Ethiraj, the management of Ethiraj College for Women is very much committed to encourage and develop a culture of research within the college. And for this purpose, we have created ECRI, or Ethiraj College Center for Research and Innovation, with whatever the possible finance support to handhold all those faculties and students who want to actually do some experiments, or who want to research or have some innovative thinking. Members of the trust board, on behalf of the members of the trust board, I wish to extend a very warm welcome to all speakers of the seminar. Our special thanks to the Chennai chapter of Science Congress Association for having joined hand with Ethiraj College for Women to organize this international seminar. My very best wishes for the success of this seminar. Thank you very much.
Thank you, ma'am.
Yeah.
I take this opportunity to invite Madam Principal, Dr. Mrs. S. Gode, to felicitate the event.
Good morning to one and all present. To learn, to unlearn, do the experiment, experience, analyze. Let this be our motto in Ethiraj College for Women. Welcome to one and all present for the international workshop to be conducted by the Physics Department of Ethiraj College for Women. Physics Department was incepted in 1948 as an allied department. We used to learn potential energy, kinetic energy, etc. Now, the transformation to space energy, clean energy, astrophysics, nanomaterials, etc. is only because of the great teachers, former teachers who have given us a very strong foundation, and our students who have taken us to greater heights. I salute, I give my fullest pronounce to all of them before we start our international online workshop. We have the vibrant Astronomy Club of Ethiraj College for Women doing wonders, motivating the students, attracting them, and they learn a lot about astrophysics. I'm very happy that we, the teachers, inculcate the scientific temper among the students by celebrating the National Science Day, our Sir C.V. Raman Day. Not just one day in a year. Throughout the year, we conduct many events, not alone for the science students, for all our students of Ethiraj College for Women, and also intercollegiate, interdepartmental programs. This creates a great scientific temper in our students. I'm sure that the young budding scientists of Ethiraj College for Women, our students, our Ethirajians, will one day become Nobel laureates that is only in our hands, and Ethiraj College for Women will support them to the maximum to grow up. I'm sure that our teachers have put in a lot of research thanks to the Ethiraj College Trust Management, who has created our dream project, ECRIC, Ethiraj College Center for Research, Innovation and Creativity, which is doing wonders for the past 2 years. And we have lots of plans to do it further in future. I'm sure that the research culture in Ethiraj College is growing to greater heights because of this. And I'm very sure that we are celebrating Science Day throughout the year. This is because of the research culture in Ethiraj College for Women. I'm very happy that we have collaborated with ESCA, Indian Science Congress Association. And I welcome Kashmir Raja, who is the convener of ESCA, Chennai chapter, and Professor Muthamil Chelvan sir, Vice Chancellor, SRM University for Science and Technology, is the executive member, and other executive members who have joined us, and Alagiri Raja sir, who is the treasurer of the ESCA. I remember how Professor Raman did a great research in a small place in Calcutta, right from 1914. He didn't grudge saying that we don't have this, we don't have that. With the small instruments, tools, with just glass plates, right, a telescope, etc., was constructed by him, and he gave us to the world the great Raman spectroscopy. Even today, we do it as a routine analysis, and we learn a lot about the materials, nanomaterials, etc., from Raman spectroscopy. I take this opportunity to thank our Ethiraj College Trust for giving a lot of support and guidance to create the research culture in our college. And big thanks to all the board members, and special thanks to our chairperson, Tirumati Chandra Devi Thanigachalam Madam. I'm sure that many great scientists will come from Ethiraj College because of all this. Thank you very much, Madam. And I take this opportunity to felicitate the Department of Physics, Ethiraj College for Women, for the dynamic team who has taken up this international online workshop for 2 days. But we are going to visit many centers, about 8 to 10 centers, and learn what is happening in other places. And as I said, we learn and learn, and the process is a continuous process. Thank you very much. And a big thanks to all the active participants, teachers, or students. Thank you very much. All the best for the success of the international online workshop. Thank you very much.
Thank you, ma'am. Your words of wisdom never fails to encourage us in achieving the mightiest targets. I would now like to invite Dr. Mrs. D.B. Usharani, Vice Principal Aided, to felicitate the event.
Good morning to one and all present here. I am very, very happy to be a part of this two-day international conference being organized by the Department of Physics in association with Indian Science Congress Association, Chennai chapter, and SRM Institute of Science and Technology. First, let me take this opportunity to congratulate the head of the department. After looking into the invite and the overview, after hearing to the overview of the two-day workshop, I am very, very happy that many of the speakers with international standards have been invited for providing knowledge in the field of nanoculture and nano culture, as well as nanomaterial and astronomy, space astronomy. Here I have to thank the management for providing a lakh and more for buying telescope for the astronomy club, and to the members who are in great number, who are participating in great number. I have to state here that the college has taken up energy audit in our institution. That itself shows the commitment of the college, not only in research, but also exhibiting its role in energy audit. Now, the effort put by the head of the department and the staff members need to be congratulated, because every time they come over to the office bringing a letter and sending it to the management, to ma'am, they will give the objective and the outcome, and the management is very kind enough to accept and have been providing financial and all the support that is very, very essential for the development of any department for that matter. And physics department has taken up the initiative for organizing this 2-day workshop for the students of their department, and also many of outsiders have also joined. I am very, very sure that the students who are participating in this 2-day workshop will definitely gain much knowledge and also proceed with the further research in the field of nanomaterial as well as space astronomy. I have to definitely state here, with the tight schedule of the head of the department and the staff members, I requested the head of the department to be the coordinator for sending a proposal, BSTA query proposal, and she has coordinated with the 10 science departments, and we have sent the proposal. Congratulations to the head of the department, Dr. Joni Virgila, and her entire team. Education doesn't mean only teaching in the class. You have to definitely help the institution, help the students in all possible way, and that is being done by the head of the department of both aided as well as self-supporting physics department. So on behalf of the management and on my own, I deem it a pleasure to congratulate each and every one of the professors, the institutions, various institutions, and the Indian Science Congress for associating with the Ethiraj College and making this day a great one. Thank you and all the best. And my heartfelt thanks to all the speakers who are going to deliver their lecture in the next today as well as tomorrow for the fullest satisfaction of our students and researchers. Thank you one and all.
Thank you, ma'am. Now I invite Dr. A. Alagiri Swami, Treasurer, Indian Science Congress, Chennai Chapter, Faculty of Nanotechnology, SRM Institute of Science and Technology, to felicitate the event.
Good morning to everybody. Can you hear me?
Yes, sir. Yes.
Okay. I am Dr. Alagiri Swami from SRM University. Actually, I have been participating working in the Indian Science Congress as a treasurer for more than 7 years, since 2015. So, Professor Muthamal Chelvan currently is a vice chancellor. When he was the director, he requested us to take care of as a job as a treasurer. So initially, I thought of a treasurer just like a calculation, like A plus B is equal to C. Then later on, I realized that we have ethical responsibility and contact people, writing a proposal, then getting the utility certificates, go to the bank, and I learned a lot of things. So it really gives me immense pleasure that we learn a lot of things apart from the teaching part. So just now, Professor Usha Rani, she mentioned that education is a highlight, and I rephrase a statement: education plus entertainment, entertainment, that is also needed, and that is one of the programs that we run for it. So she mentioned to us that it is affiliated with the Indian Science Congress, but I feel that privilege, we are also joint partner with Ethiraj College. But one thing I just recognize here, after listening continuous discussion by chairperson, then principals, then other organizers and management and students, including students, I feel that hierarchically arranged, and something called a brain drain. Brain drain means we try to understand each and every part, and we try to gather energy from them, all of them, and still we have enough chance to look for all the people. So this the title is highly suited nanomaterials and green energy, and utilize the energy from the space at astronomy. So indeed, for the past 1.5 months, we have been discussing with Mahalakshmi. So Mahalakshmi is not new to me, and actually just I'm sitting here in the cabin, and next cabin Mahalakshmi cabin, she worked here, and Dr. Mohan Raj is also. Actually, he was alumnus of SRM University. Whenever the professor Sadish Krishnamurthy used to visit in Chennai, so he used to visit. So we have interconnected. So I thought that 3 or 4 members are known, and but right now when I look at the numbers, 200, more than 240 members. So room is full of audience. Then we have to be very happy for this. So regarding that, we have started with some ideas. We can conduct a program. So I have been discussing with Mahalakshmi for a long time, more than 2 years actually. So if I remember, I think nearly 2 years have gone. Then I discussed with Mahalakshmi to start up with something else. Then finally she came with an idea that we can go for the international conference. Usually Indian Congress Chennai chapter don't recommend foreign, that means international conference, but we consider the part of the programs, and it is our aim to go for only the students who are the weak society or socially disabled or well able students. We can go for it. So I hope the society will gain knowledge of this. So as far as my knowledge is concerned, ISCA, Indian Science Congress Chennai, I'm sorry, Indian Science Congress Association is located in the head office is Kolkata. So it was started somewhere around nearly 100 or 115 years. It was that Indian Science Congress Kolkata office, head office, that was started 100 years, nearly 100 years by the British people. Later on, they want to promote and inculcate the scientific temper amongst the students, mentors, and all the people, that means society. They thought at starting of the chapter. Chapter means they can allocate to the funds, and then members, they affiliate some members, and I think around 28 chapters are there. So here we have Chennai chapter that is located just above. I'm sitting on the 6th floor. So 9th floor is the head office in Chennai office, and one more chapter in Coimbatore. So we have 2 chapters in Tamil Nadu, and the closest chapter is Pondicherry, Puducherry. So initially 3 or 4 years back, we thought of conducting programs only in Chennai or otherwise the nearest areas. So then we thought of extending some areas to Madurai and Ramanathapuram and Kanyakumari. So we have successfully conducted some programs in Madurai and Ramanathapuram, Kanyakumari, and other places. So a little bit extended. So one day we had a chance to meet Indian Science Congress president. He said, no problem. We can. The purpose of arranging the programs not only in Chennai or in around areas. So the idea is we can try to go for the other places. But some drawbacks. Actually, we have brighter area as well as a darker area. So brighter area, there are so many things. Chennai chapter leaves a lot of footprints among the society. But the darker area means, for example, we are conducting the program, but I'm not there. Physically, I'm not presenting there. And unfortunately, the convener is out of country. He was not able to communicate, or is not able to come in the middle part of the day, midnight. Then other person is also busy with these other works. So that is the one, I can say, one dark area that we are not able to meet each other. And that could be a disseminate knowledge and know knowledge to all the society. So I really thank the management. I really thank the organizer who have done that's why I mentioned the drain. And we have a lot of members like session members, then Congress members, then life member also. So every year we used to conduct life member association fellowship, at least 2, one from middle part of the Chennai and other from outskirts. So we try to conduct the 2 we nominate. But as you know that this is the COVID time, so we are not able to send those persons outside. So that is a drop. So right now, this is the 8th workshop. This is the 2nd day workshop. This is the 8th workshop we conduct on the online, that means COVID period. And 3 more workshops are there. And we'll wind up before March, and we try to submit the report. So I really thank all the people and management and the speakers. I welcome the speakers and for green energy and especially the nanomaterials and space astronomy. So the moment I discussed with Magalakshmi why I thought that why space astronomy, then later on I realized that nanomaterials start with zero and like mathematics, and space astronomy something is universe, that means infinity. So in mathematics we can say zero and infinity are two lemmas, and we try to connect two things together. But I really appreciate the physics club and physics department that try to gather all the knowledge, nanomaterials and green energy, and let's look for the other possibilities. You can look for other possibilities. You can gather the information from them. Space astronomy also. So two different approaches. Like we can say in nanomaterials, nanotechnology, top to bottom approach and then bottom to top approach. So we try to utilize. But here I feel that bottom to top approach is always better, hierarchy order and no defects. So I wish you all the best, and I thank you very much for the opportunity given to me. I can really very overwhelmed, and I thank all the people who have joined here. Thank you very much for the opportunity being given.
Thank you, sir. Thank you very much. Now we have Mrs. Abhirami, Head, Department of Physics, self-supporting, to present the vote of thanks.
Good morning to one and all present here. The essence of science is independent thinking, hard work, and not equipment. When I got my Nobel Prize, I had spent hardly 200 rupees on my equipment. C.V. Raman. I feel privileged to extend my warm gratitude to all present here for attending the two-day online international workshop. I would like to thank Srimati Chandradevi Tanikachala, Chairperson, Ethiraj College Trust, the Principal and Vice Principals for the constant encouragement and the support extended to the department and the students at each and every step of our activities. I would like to express my sincere and deepest gratitude to Dr. S.V. Kasmir Raja, Convener, ISCA Chennai, Dr. Muttami Chelvan, Executive Member, ISCA Chennai Chapter, Vice Chancellor, SRM Institute of Science and Technology, Chennai, for their warm wishes and encouragement. On behalf of the department, and I express my gratitude to all the eminent speakers for consenting to share their valuable insights in the today international workshop. My sincere thanks also to the teaching and non-teaching staff and the research scholars of the Department of Physics for their efforts in making the event a success. I wish to applaud each and every participant from the various institutions and also our own students for their enthusiastic harmonization. Thank you, Ananda.
Thank you, ma'am. Now I call upon Dr. Mrs. S. Mahalakshmi, Assistant Professor, Department of Physics, to present the speakers of the day.
Good morning. So today we will start our first plenary session. The keynote speaker, Dr. Professor Raja Mohan. So it is with a special excitement that I'm pleased to introduce our keynote speaker, Professor Raja Mohan, Research Professor in the Chemical Industry Research Institution, University of Ulsan, South Korea. Sir has acquired his doctoral degree in the field of electroactive shape memory polymer nanocomposite actuators from Gyeonggi University, South Korea, ensuing postdoctoral research in Myeonggi University, Suwon, South Korea. Adding feathers to his hat, Sir has received Young Scientist Award by DSC SERP, Government of India in the year 2013, and Best Faculty Award by Madhya Pradesh Private University Regulatory Commission in 2018, and JNU Annual Research Award by Jagran Lake University in 2019. Professor has completed the 2 national research funded projects by DST SERP and an international research project by National Science and Technology and Innovation Plan, Saudi Arabia. To his credit, Sir has 4 Indian patents in a novel method for forming flexible multi-walled carbon nanotube foil, method for synthesis of thin silver nanowires, synthesis of nano-silver oxide by wet chemical method, synthesis of silver nanoparticles employing a new approach. His profile is boundless. Professor Rajamohan has accomplished voluminous research grants from DST and NSTIP of middling 100 lakhs. He has published several number of research papers, book chapters in global journals. So now, the speaker will be introducing. He'll be giving the talk. Thank you. Have a great day.
Good morning to everyone.
Good morning, sir.
Good morning. I think it is an audible.
Yes, sir. Yes.
Okay, thank you very much. I would like to present the topic on metal oxide hybrid nanocomposite electrode for energy storage and applications, especially for supercapacitors. First of all, I would like to thank the chairperson and eminent scholars and board members and faculty and student and research scholars. First of all, in this topic, we are going to focus on the supercapacitors, especially for metal oxide based hybrid nanocomposites. In the field of energy sources, generally it has been classified in 2 topics, either in the form of non-renewable or renewable energies. Depletion of non-renewable energies, especially fossil fuels, oil, coal, and natural gases, and etc. We are depending upon renewable energies as a non-conventional energy resources, especially for solar cells, wind, and etc. We are depends on more number of energy storage devices due to it has to be more portable, and our demands in the form of transportation and small applications, etc., either in the form of wearable or non-wearable devices, or as a commercial and domestic aspects. Generally, in supercapacitors, it has been classified 2 headings, either in the form of electric double layer capacitor or pseudo capacitors, the combination of both electric double layer and pseudo capacitor as a hybrid capacitors. Electric double layer capacitors, it is mostly in active materials, activated carbons, carbon aerosols, carbon nanotubes, graphene, and the pseudo capacitors mainly based on metal oxides and conducting polymers. As a hybrid capacitor, the combination of both carbon-based as well as metal oxide or conducting polymers, the combination of as a hybrid composites.
Excuse me, sir. Sorry to interrupt. Your
Yes.
slides are not changing, sir. It's still in the first slide.
Okay, sorry, just a minute.
Yes, sir.
Seconds, Reda.
Now, can you able to see the slides?
I see the supercapacitor slide, sir.
Yes, 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 yes. So the supercapacitor already I had mentioned it is having the main classification in the form of electric double layer and pseudo capacitors. The combination of both the electric double layer capacitor and the pseudo capacitors to form as a hybrid capacitors with the presence of carbon based materials either in the form of carbon nanotubes or graphene or activated carbon with the presence of metal oxides or conducting polymer to make as a hybrid composite in the form of hybrid capacitors. Here they're having both mechanisms. It will be act either in the form of electrostatic charges or electrochemical reaction in the form of electrochemical storage reactions also occur in the hybrid capacitors. The ceramic capacitors generally is a normal capacitors available in commercial market. Everyone has been seen in your normal routine life in your home or shop or whatever it is. The ceramic capacitors generally is made up of two electrodes. Is a metal electrodes um, with as a dielectric material in the form of ceramic films has been used as a dielectric material. It is simply has to be electrostatic discharge and to density of the charge density has been accumulated in the electrodes while you are applying that voltage in between the potential. The electrodes have been accumulated the electrostatic discharges. It has been used for various commercial applications, but in the point of supercapacitor as a hybrid capacitors, the combination of both electrostatic discharge as a electrochemical reactions similar like as a battery while it's a charging and discharging as a electrochemical reactions going to occur. The same similar pattern and mechanisms happen in the hybrid capacitor also, the both electrostatic as well as electrochemical reactions. Generally electrochemical energy storage systems, it has been the terms, using the terms as a technical terms generally for the energy density as well as power density. Energy density is a measure how much energy as a electrochemical system, how much energy can be able to store in the device, that is called as a specific energy or energy density. For example, as a 1 liter bottle, it can be able to store in the water bottle, it can be able to store 1 liter. It is a specific energy, and at the same time, how much energy is going to deliver from that device, that is called as a power density. The how much of water can be able to pour it in. The same the picture has been mentioned. So the power density and the energy density is the basic measuring for the device, especially for the energy storage devices. Either it can be applicable for the supercapacitor as well as it can be applicable for the batteries. Any type of batteries, either non-rechargeable battery or rechargeable battery or lead acid batteries or lithium batteries and etc. Same like supercapacitor also, it can be applicable the same energy density as well as power density. It can be applicable for this ceramic capacitor or supercapacitor or a hybrid capacitor. It can be applicable. What are the advantages compared to the batteries? Supercapacitors. Supercapacitors, it can be classified four categories in the form of performance and economics, sustainability, and safety. In the point of view, in the high performance, it is in a high power density compared to battery. It can be able to charge and discharge very quick and a high charge current compared to battery, and the lifelong of supercapacitor as a capacitor It's a very long time durations compared to battery life. And the economic point of view, it is a low cost and hybrid solutions in extended life, low maintenance, no active management is required, efficient on cloudy and rainy day, always available the energy. And the next one is sustainability. There is no any corrosive material or acid or toxic fumes are not occurring. Suitable for global and customers, and no damage with the deep discharge, and it can be able to recover from the long ideal period. For example, if you are not able to use for the long time period also, it not able to damage, and you can able to reuse it on multiple number of times. The longer period and the safety, the no fire hazard and no toxic emissions, and eco-friendly and recyclable. Just I would like to give us a few examples for the supercapacitors applications, because you might not observe the availability of the supercapacitor in commercial market, but these are the commercial market and it is available in the current our normal lifestyles. We are using as a supercapacitor in the form of mobile phone, tablets, and laptops, LED devices like DVDs and etc., and digital cameras and flashes, wearable devices, and photovoltaic cells, especially for storing, and the same like wind power mill and supercapacitor equipped dram available in Brazil, and EV vehicles, electric screwdrivers, GPS system, and etc. Just I had shown as a few examples. You can get as an idea where it can be usable, the availability, and as well as the place of applications. It can be get idea. The next one is nanomaterials. The nanomaterials, generally nano is a size scaling unit, 10 power minus 9 meter. The range of materials, especially as particles, from 1 to 100 nanometers in the classification of nanomaterials. So more than 100 nanometer, it is not under the classification of nanomaterials. What are the advantages why we have to focus on nanomaterials in energy storages? The main advantage in nanomaterials in energy storages, it has having the large surface area, easy to absorption and storage of electrolyte ions, and plus high contact area between the electrode and electrolyte, maximum active sites for the reaction. It is understood for as a large surface area. The next one is the manganese oxide, MnO2. For this lectures, we are going to focus on two different metal oxides. One is in manganese oxide, another one is a ferric oxide as a ferrite. So manganese oxide is a tetragonal, MnO2 as a unit cell. The same basic unit as a MnO6 is a octagonal. It is a p-type semiconductor with a band gap of 1.3 electron volt. The theoretical capacitance of manganese oxides in the range of 1380 farad per gram. The charge storage mechanisms, mainly while charging, the manganese oxide is converted into manganese oxide plus hydroxide. Again, it's going to discharge, is converted in the form of manganese oxide instead of manganese oxide and hydroxide. And the properties, it has been we had mentioned already, and it is naturally abundant and low cost and not toxicity and multiple oxidation state. The next one is ferric oxide. So alpha ferrite is a rhombohedrali centered hexagonal center of corundum type. It is a N-type semiconductor. The band gap a little bit higher than manganese oxide. It is a 2.1 electron volt. Schematic display the theoretical specific capacitance, the range of 3625 farad per gram. The charging mechanisms, the ferrite is converted into ferrite hydroxide while charging. Again, Discharging its ferrite hydroxide to convert in the form of ferrite. This is a natural abundance, low cost, and non-toxic, and multiple oxidation state, similar like as a manganese. Carbon nanotubes. Carbon nanotubes, it is an allotropy of carbon. It is a crystalline material, and it has been fascinated towards, especially for material science, remarkable properties, mechanical, chemical, as well as electronic properties. It has been constructed by graphene sheets, rolled sheet of graphene sheets, to form as a single wall and multi-wall and double wall carbon nanotubes. CNT has the strongest and most flexible known molecular, is made up of C double bond covalent bonding, and they form a hexagonal carbon network, form as like a tube-like structures. First, it was discovered in 1991 by Ijima. This is 10 images of single wall carbon nanotubes. This is a double wall carbon nanotubes. This one is a multi wall carbon nanotubes. The diameter is 3 nanometers. The property of CNT, Young's modulus, already I had mentioned, it is having very good mechanical properties. Young's modulus in the range of 1 terapascal, and superconductivity at the low temperature, high thermal conductivities in axial directions, high surface area, 1315 meter square per gram. CNT is a nanocomposite provided structural and functional capability, different chemically, and CNT with a different conductive property, especially the rotation of the CNT sheet as a graphene sheet. It has to be as an armchair and a zigzag or chiral. It's going to change the property of electronical property, especially the armchair property. It will give in the form of metallic behavior. Metallic, the conductivity is similar like a metallic, and the zigzag pattern it will be give in the form of semiconducting, and chiral it will be same like a semiconducting. Especially multi-wall carbon nanotubes is a metallic behavior compared to single wall carbon nanotubes. The contribution of CNT in energy storages. CNT, it has to be created in a network within the composite. Electrical conductivity is very good electrical conductivity, as well as reinforcement to the active materials, and mechanical stability to the nanomaterial, that is the active materials, and the large surface area for the electrochemical process, and lightweight and highly chemical stability that allows resistance towards electrode surface degradation. And especially for CNT, electrode material can be confined a small area to increase the electrolyte and electrode contact. And the porosity property of the and the entanglement and the structure of CNT allow the penetration of electrolyte into the material to accelerate the diffusions. Now we are going to see the manganese dioxide based hybrid nanocomposite coated as a cotton electrode for energy storage applications. Here I had used as a cotton electrode is the main advantage. Cotton having as a porous structure and a highly flexible substrate. So the interaction of that highly and porous property with availability of active material to enhance their absorption of electrolyte, to increase their storing capacity. That's the reasons I had used as a cotton electrode for my research work. The preparation of manganese dioxide hybrid nanocomposite had used as a multi-wall carbon nanotubes with the presence of manganese acetate. Here I had used as a sodium hydroxide as a reducing agent. With the presence of sodium hydroxide, manganese acetate to converted in the form of manganese ion, and the sodium hydroxide to react with the acetate to form as a sodium acetate. At 100 degrees Celsius, manganese ions to convert in the form of manganese oxide with the presence of atmospheric oxygen and the presence of water to convert in the form of manganese oxide at 100 degrees Celsius. The decorated manganese oxide
Sir, sir, am I audible to you? Your mic is muted, sir. We're not able to hear you. You're still muted, sir.
So if you have number, you can call him and that will be better. Or message him.
Yes, sir. Yes, sir.
From which slide it is not audible?
The previous slide, sir. The previous slide.
Okay. Okay. From this slide.
Yes, sir.
Okay. So once again, I repeat that one. Preparation of a manganese dioxide based hybrid nanocomposite. Here I had used as a multi-wall carbon nanotubes with the presence of manganese acetate and the sodium hydroxide act as a reducing agent. Sodium hydroxide is a react with sodiums react with acetate group to form as a sodium acetate, and the manganese ion to form in the surface of the multi-wall carbon nanotubes as a manganese ion. At 100 degrees Celsius, to convert the manganese ions to convert into in the form of manganese oxide as a decorated manganese oxide, decorated multi-wall carbon nanotubes. After the preparation of that active materials, it can be made as a slurry with the presence of PVDF as a 3% and a 97% of active material. DMF act as a solvent to make as a slurry. Here cotton as a substrate, as a pure cotton cloth. And before coating, it has been cleaned and it has been washed with multiple number of distilled water and washed with ethanol and acetone, dried in a vacuum oven. The substrate has been cleaned before the coating the slurry. After the cleaned the substrate and the coated the slurry, the material has to be dried at vacuum oven at the temperature of around 80 degrees Celsius. Once you complete the drying process, the electrode has been used directly as a electrochemical studies. Before going the electrochemical studies, we had that active material has been characterized with several characterizations, including SEM, TEM, and etc. Today, I am going to show the few characterizations instead of all details because due to the time consuming. The first one I would like to present in the transmission electron microscope. Here we can able to see the multi-wall carbon nanotubes with ferrite, with the manganese oxide to interactions. The manganese oxide grown the surface of the CNT. It is in agglomerations. There is no any uniform distributions, but it is in agglomerations. But in that agglomerations, the size of the particles, it is in the range of 50 nanometer. But here is more highly crystalline nanomaterials. Here you can able to see the grain boundaries of manganese acetate compared to other samples. Here we can able to see the grain boundaries. It is a highly crystalline manganese oxide has been grown the surface of the multi-wall carbon nanotubes. It is like as a coating on the CNT surfaces. The next one is an XRD. XRD generally has to be used for to study that crystallinity as well as crystalline property and the Miller indices, the phases, and sometimes it can be able to we can able to analyze the impurities also less also. Here, plus additional point of view, from the XRD, we can able to calculate that particle size also. The average particle size we can able to calculate from that XRD. And the main advantage, and from the XRD also, we can able to make as a partial conclusion the particle has been either amorphous or crystalline, as well as the particle has been in a macro or nanometer range. The mainly the wide range of peaks mainly depend upon the nanomaterials. If we're having narrow peaks are represent for highly macro size or millimeter size or something like that. But in the wide peaks are always represent for as a nanomaterials, nano range, in the range of nanometers. The blue color denoted numbers, it is represent for as a carbon nanotubes. It is 002 as a represent, especially for the represent for the CNT as a graphite phase as a 25.6 degrees in 2 theta, and the remaining peaks are represent for as a manganese oxide. After that, by Debye-Scherrer equations, it has been concluded it's a range of around the 80 nanometer. It has been calculated. K denoted for the crystallite shape of the shape factor, and lambda is the X-ray wavelength, and beta is a full width and half maximum, and the cos theta is a de Broglie angles. From that, Debye-Scherrer equations and calculations, so it has been concluded the particle has been the range of nanometers is not above 100 nanometers. It is a range of nanometers. It is around 80 nanometers. After that, the sample has been analyzed by the X-ray photoelectron spectroscopy. Generally, it is mentioned as a XPS. XPS has been used for us to calculate the binding energy of the complex materials. It can be able to see the material has been which oxidation state, as well as either it is oxidized or non-oxidized state also we can able to analysis from the XPS. Here that first XPS has been in that range from 200 to 1000 electron volt, and the range of 284.9 electron volts is represent for as a carbon peak. As a pure CNT also here having available. There is no any additional peaks compared to that manganese oxide with the CNT. And 529.6 is represent for as a oxygen peak, and 641 and 652 it is represent for as a manganese 2p 3/2 and manganese 2p and 1/2 is a binding energy of manganese and manganese oxide. The range of separation spin is in the 11.7 electron volt. It is in the range of it is presence of manganese oxide, and oxidation state it is generally in the range of 4 oxidation state of manganese 4 plus. After the sample has been characterized in electrochemical characterization, I had used this biologic 150 SP potentiostat. It has generally they are tried with 3 electrode systems. One is in a reference electrode, another is a counter, another one is working electrode, whatever we had prepared as the presence of active materials. And we had used electrolyte as a 0.5 molarity of sodium sulfate as an electrolyte. And the sample has been holding, and it has been tested for various electrochemical studies. So we are going to see that what kind of electrochemical studies has been done. One is in a cyclovoltammetric studies. Cyclovoltammetric studies is similar like a charging and discharging only. Here the sample has been in the voltage range, the potential range from minus 0.6 volt to 1 volt. Here while charging from minus 0.62 volt to the material has been get the charging the materials up the range of in the 10 milliamp. The current is occurred around 10 milliamp. Again, it going to discharge is bag. Again, is going to discharge here from 1 volt to again minus 0.6 volt. It can be done for various number of cycles. So from these cycles, we can able to calculate the how much specific capacitance of the specific the samples. We had two different samples has been used, either is a non-calcine or a heat treated, the calcine samples. The heat treated sample has been shown the better result compared to non-heated samples, mainly because of the heat treatment to enhance the crystallinity property of the metal oxides. It will be enhance their electrochemical behavior, the crystallinity behavior to enhance the electrochemical behavior. So the non-heated sample is around 213 farad per gram, but heated samples it has showing around 634.35 farad per gram. So they're having drastic difference between the heat treated and non-heat treated samples. So the calcinations to enhance their property of the electrochemical property. So it has been done various number of cycles. It has been around 1,000 cycles has been done to study the measurements and the stability of the samples, how much the sample has been stable, and as well as the electrolyte. This is a GC measurement. The sample, the potential we have to keep as a constant current, to check that voltage as varying the voltage, and the number of cycles. In the number of cycles, we have to change either charging and discharging. We can able to analyze again here also we can able to calculate the specific capacitance of samples. It is in the same range of whatever we had calculated from CV. It is also in the same range around 204 farad per gram and 622 farad per gram. Here it has been light IR drops due to the electrolyte ion diffusions in the cotton substrate, and as well as folding conditions also. We had did with the folding conditions. The sample has been folded. How it has been folded condition, the storing that mechanisms happen. It has been studied in that electrode, especially for cotton electrode. Around 1,000 cycles we had did for this kind of studies. From that result, we had concluded the specific capacitance in the range of 600 farad per gram, and for heated sample and non-heated samples in the range of 200 range of farad per gram. The next one is cyclic performance. Here we had did around 1,000 cycles. So in the 1,000 cycles, the sample A it is represented as a heated sample. Sample B is represented for non-heated samples. The heated samples having that better stability compared to non-heated samples. The retention of that cyclic retentions are around 84% of cyclic retentions is available for as a specific capacitance. As a conclusions for these samples, compared to the previous studies, it has been having 84% of retention, and the specific capacitance in the range of 634.3 farad per gram. The next work is a ferric oxide based hybrid nanocomposite. Here I had used as a dry shell bottle guard as an electrode substrate. And the previous one is we had used as a cotton, and here we are used as a dry shell bottle guard, and the active materials as a ferric oxide based hybrid nanocomposites. Ferrite multi-wall carbonate, ferrite decorated multi-wall carbonate has been synthesized by same wet chemical synthesis. The ferric chloride has been used as a ferrite sources, and sodium hydroxide has been reducing agent with the presence of 100 degrees Celsius. The ferrite Fe ion to convert in the form of ferrite to decorate in the surface of the multi-wall carbon nanotubes. The active material has been coated in dip coating method in the dry bottle dry cells by dip coating method in multiple number of coatings. There has been around 10 coatings has been done for the samples. The next one is a transmission electron microscope. Here it is, we can able to see same as a agglomerated samples. So we are not using any surfactants to it maybe minimize that electrochemical property of the sample. So we are not using any surfactants. So without surfactants, the material has been agglomerated, but it has been some particles also, but in the range of nanometer. The X-ray we had data for that CNT and ferrite. Already I had mentioned it is that 002 plane is represent for as a graphite plane for the CNT. It has been represented, the sample has been interact with CNT as well as ferrite, a composite. It has been justified from that result. The remaining peaks are represented for as ferrite peaks. The crystallinity, the size has been calculated from the Debye. It is in the range of 100 nanometer. It can be similar to that. That result has been justified by the results. The XPS spectroscopy in ferrite at the 711.2 electron volt and 724.7 electron volt with the spin energy separations, 13.5 electron volt. It has been represented for Fe2p12 and Fe2p32. It is represented for as a 3 plus ions, Fe3 plus ions, Fe3 plus ion presence in the ferrite samples. In cyclic voltammetric, we had the samples in the different ferrite loadings. For example, 1% and 2% and 3% of ferrite samples along with the CNT. CNT is a constant loading. And to increase the ferrite loading to check that electrochemical behaviors in the range of potential range in the range of 0.2 volt to 0.7 volt with 0.5 molarity of sodium sulfate as electrolyte with a multiple number of cycles. It has been justified from the multiple number of cycles. The CNT with the ferrite, 1% of ferrite sample loading in the range of 278 farad per gram, and compared to ferrite 2% is having 492 farad per gram, and 3% is having higher, around 885% of farad per gram. So after that, from that CV, the high loading of ferrite has been better specific capacitance compared to the lower percentage of ferrite samples. But in the case of same, it has been represented for charging and discharging also. Charging and discharging here we had used for as 10 amp, and this one is 40 amps has been used. And the potential range it is around 0.8 in the range of 0.7 voltage. While charging and discharging, the discharging time, it's taking long time period, especially for 3% weight loaded as a ferrite samples compared to the 1 and 2% samples. And the 3% has showing some little bit higher drops compared to that 1 and 2%. The specific capacitance in the range of it is represent similar to the CV. 200 and 400, and especially for 800 farad per gram. The cyclic performance of a ferrite sample has shown the better result in ferrite samples. The retention of a 3% sample has been shown around 81% compared to 2% and 1% samples around 1000 cycles. In that, from that conclusions, the 3% samples of 3% loaded ferrite samples has been better electrochemical property compared to 2 and 1% of ferrite samples. The main advantage from the conclusions, the bottle guard frames has been provided easy diffusions and electrolyte and ions. It is a spongy and porous natures, and the CNT serve as a flexible network for the fast charge transfer, and the CNT provide a mechanical strength to the electrode, and optimal loading of active essential for ferrite 2% is having optimum load compared to the 3%, and it has been shown the excellent capacity as well as good cyclic stability of the conductivity. The comparative table of CNT with the ferrite nanocomposites, it has been shown the better result compared to the previous works has been done for other researchers. And the previous researcher has been shown for the specific capacitance in the range of 200 or 192 farad per grams, but it has been shown in the range of 492 farad per grams. The cyclic retentions are around in the range of 77, 78 percentages. The summary of this work, the metal hydroxide nanocomposite were successfully synthesized using as a scalable and effective precipitation method, and hybrid nanocomposites were fabricated by biosubstrate is eco-friendly, and the biosubstrates are easily available, lightweight and eco-friendly, and non-toxic materials like as nickel or other metals. We are not using heavy metals, and it is main advantage. It has been porous and spongy and networking highly networked structures to allow the maximum absorption of electrolyte, and it's allow easy diffusion of ions in active materials. And with the presence of CNT provide the mechanical and the strength and the substrate confirm the structural stability, even maximum number of the cycles. After this one, I like to show some my previous other works also. It has to be some interest for the student to, especially for the research activities, in the form of my research highlights. The next one is shape memory polymer as a nanocomposites. Shape memory, everyone knows about that one. It's a functional materials. It's mainly depend upon that polymers having the TG of the polymers as key parameters. It's a depend upon TG either in the room temperature or above slightly room temperature. It can be used for as a various commercial aspects applications. Here I had used as a polyurethane TG in the range of 60, and PVDF and PLA and PBS also in the range of room temperature TG in the range of 60 degrees Celsius. So that is the main key for asset to making a device of shape memory polymers. And the polyurethane act as a matrix, and pure CNT as well as surface modified or metal functionalized as a MCNT has been used as a filler material as well as reinforcing agent. At 180 degrees Celsius, by melt mixing process, the composite has been fabricated in the form of sheet-like structure. It has been used for various characterizations, including for SEM, this is FE-SEM, and conductivity study as a surface resistance, as a conductivity study, and the shape recovery time versus temperature, as well as shape recovery ratio in number of cycles has been studied, especially for metal functionalized CNT and along with the polyurethane as a matrix. The metal functionalized CNT has been shown the better distribution of CNT in the polymer matrix compared to the pure CNT. The dispersion of CNT is very poor compared to the metal functionalized CNT. And same like conductivity also very poor because of very poor dispersion in CNT in polyurethane matrix. So pure CNT having very poor conductivity compared to metal functionalized CNT. The shape recovery ratio has been number of cycle has been studied around 50 cycles, and that silver functionalized has been shown better result compared to the copper functionalized samples. Same like recovery time versus temperature, the recovery shape recovery also. It is a fast recovery, silver functionalized, copper functional little bit slower, and pure CNT, it is having longer duration compared to the both the metal functionalized samples. This is U-shaped samples to recover to the linear structure at DC 40 voltage of DC power supply. In 12 seconds, the sample has been recovered to the original shape as a linear structure in 12 seconds. This is another work, this is a flexible transfer and conducting film with the presence of CNT and multi-wall carbon nanotubes. In solvent has been used as a THF solvent has been used around different loading multi-wall carbon nanotubes loading in a different weight percentage, and coated on the PET substrate with spray coating or filtration technique. Has been coated and it has been used as a flexible transfer and conducting film. The surface resistance around 68 ohms per square, around 98%, 90% of the transparency. So it can be used for various applications. It can be used for various kind of applications for touch screen and flexible devices, flexible electronic devices, and etc. This is another one, is a flexible CNT foil. It's a pure CNT without any binder to form as like a seed form for using as a thermal interface material as well as electrode for energy storage applications also. And it was a file the pattern in Indian patents. And after that, I would like to show some instrumentation facilities available in my lab. Some atomic force microscope is available. So it can be able to study for the surface topography of the materials, either powder or solid materials also we can able to study from that atomic microscope. And we have the facility of TGA and DSE. TGA has been used for thermogravimetric analysis, same for polymeric materials, and the DSE also has been used for as a polymeric materials. Differential scanning calorimetry, so we can able to study the crystallinity, and the sample has been thermal stability. TGA has been used for the thermal stability of the sample, how much temperature is going to withstand. Degradation ratio also we can able to study. And the DSE has to be used for mainly for as a crystallization of the sample, so we can be used the multiple number of crystallization, and TG and the crystallinity and melting point also we can able to study from the differential scanning calorimeter. Then we have the facility of FTIR, UV spectroscopy, and universal testing machines, and photolithography available to design the microstructure of the samples to making as a master mold for fabricating different kind of applications. Here we are using as a photolithography for developing as a E-skin for electronic skin, for a microstructured electronic skin for various kind of applications, sensor and etc. And we have the electrochemical illustrations and the contact angle measurement. The contact angle measurements mainly has been used for as a surface, either in the form of hydrophobic and hydrophilic properties. So contact angle measurements are available. And some other things like as a spin coater and UV plasma cleaning, and the humidity temperature measurement, and ball milling for as a mixing of inorganic materials like metal oxides, activated carbons, and graphene, emcenes, and etc. It can be used for as inorganic material. So it can be used for the functionalization for different applications point of view. Thank you. Do you have any questions?
Yes, the participants are requested to pose their questions either in the chat box or in the question answer section.
So very good morning, sir. Thanks for a wonderful presentation, sir. Myself, Dakshna.
Yes, please.
Sir, I have one question for you. Can you hear me, sir?
Yes, I can hear you.
Sir, I have a small query, sir. Yes, sir. Why is the potential is different in the CV and the GCD, sir? In this, I mean, in your second, the bottle gourd experiment, sir. In the CV, the potential difference were up to 0.3, but in the GCD, it was up to 0.6. May I know the reason, sir?
Just a minute. No. Potential here we are using for as a 7.7 volt. 0.7 volt only. We are using as a 0.7 volt.
Okay, sir. Here in the CV, it is.
No.
Okay, here it is.
CV they had mentioned in the form of to minimize that graph it has been missing. So it is a 0.7 volt one.
Okay, sir. Similarly, in GCD also, it is up to.
For 0.7 voltage. We are using as a 0.7 voltage. It's coming 0.7.
Okay, sir. Okay, sir. Thank you so much, sir.
Okay.
The participants can either raise their hands or pose their questions in the chat box. The speaker will be answering them shortly. The feedback link for the session is present in the chat box as well. So we have a question in the chat box. What is the effect of electrolyte molarity? Participant wants to know what is the effect of electrolyte molarity.
Mr. Ganesh asked for that. What is the effect of electrolyte molarity? Electrolyte molarity is mainly it has to be how much the energy, the presence of availability of ions, the mobility of ions. If we're having the less molality, having the availability of ions will be less compared to the higher molarity. So mostly it has been moderate. It is in the range of 1 molarity to 0.5 to 1 molarity is a moderate. It has to be used for as a laboratory functions as well as it going for as a to making in the form of devices. So that is the main key parameters. If we're having less molarity, the availability of that mobility and availability of that ions in the electrolyte, so it will be very less. So interaction between the electrolyte ions will be having very less. So the charging and the discharging that specific capacitance also value will be very less.
Yes, sir. Thank you so much. We have another question from Nisha Prakash. She wants to know what would happen to the specific capacitance value if the electrolyte is changed. If yes, can you please tell the reason? Will there be any change when you change
changing the electrolyte will be the changing the specific capacitance. Yes, absolutely changing, but it is not going to much more difference. It is having the slight difference, but it is not much more differences not going to occur. But it is having the slight difference. For example, if we are using as a sodium sulfate instead of a potassium hydroxide, the potassium hydroxide it is more vigorous compared to the sodium sulfate. So it is going to give a little bit higher specific capacitance as well as some noises also will come while your studies is going to react with the electrode also. Substrate also is going to react to potassium hydroxide, especially if you are using as a metal-based substrate. For example, aluminum or other substrate, if you are using, potassium hydroxide is going to react as more compared to the sodium sulfate ions. And the same like if the sodium sulfate, the sulfate ions is a larger size compared to the hydroxide ion. So the specific capacitance point of view, the size of the ions is more size, bigger size is going to charge also is higher compared to the OH. So little bit the same result only will come, but the disturbance of potassium hydroxide, it's going to disturb that substrate, the metal substrate also is very high.
Yes, sir. Thank you so much. We have another question. It's from Joe Blessing. In case of platinum as working electrode, then what shall we use as the counter electrode? As we use platinum as counter electrode, does this cause any change or issue with the EC working station?
Just a minute, I have a question. In case of platinum as a working electrode, then mostly platinum has been used as a counter electrode. Working electrode mostly used for whatever your preparation sample has been used as a working electrode. So if you are using as a working electrode, you are going to study about the platinum as a property only. So whatever the property you are going to study, so that sample act as a working electrode. So as a default, mostly they had used as a platinum as a working electrode, and glassy carbon or AgCl based electrode has been used as a reference electrode.
Yes, sir. Thank you so much. I think that is the end of the question answer session. A request to the participants, if you have any questions, please post it in the chat box. The speaker would be answering them shortly.
Okay. Sir?
Yes.
Yes, I couldn't understand the answer. I'm Joe Blessing actually. I couldn't understand the answer. I should have to change this platinum into this glassy carbon or AgCl?
No, glassy carbon or AgCl has been used as a reference electrode.
Okay, yes sir.
Reference electrode, and platinum used for as a counter electrode.
Okay.
And the working electrode, whatever your sample prepared, the sample has been working act as a working electrode.
If I'm applying my sample into this, is it platinum coated with my sample or platinum?
Yeah, no issues. So platinum coated, even you can use as a platinum substrate and coated your active samples. Used for as a working electrode, no issues. So
still the platinum will be a counter electrode.
Yeah, still platinum will be as a counter electrode. But in the case of if you are using as a device, in the case of device, if you are, for example, you are having both anode and the cathode and electrolyte, a complete setup as a device, that both reference and counter electrode is not required.
Okay, sir. Thank you, sir. Thank you.
Thank you.
Yeah.
I guess that is it, sir. Thank you very much for this session. I hope the participants really were enlightened here. We have lots of compliments for you in the chat box, sir. Thank you so much.
Thank you, madam. Thank you very much. Thanks a lot.
Yes, sir. Participants, the feedback link for the session is posted in the chat box. You can go ahead and fill the feedback form. With this session comes to a conclusion. Now I call upon Dr. Mrs. Abhirami, Assistant Professor, Department of Physics, Self-Supporting, to invite the next speaker. With this, the first session comes to a conclusion. I now invite Dr. Mrs. Leela from the Department of Physics, Self-Supporting, to invite the next speaker.
Good afternoon. Good afternoon. I'm happy to have this chance to introduce to our guest speaker this afternoon, Ms. Bhavana Lalchand. She is currently pursuing final year doctoral program at the Institute of Astronomy, Taiwan. She has completed her master's at WCC, Women Christian College, Chennai, and Tamil Nadu, and has also worked as an assistant professor in various colleges in Chennai. She has secured 76th rank in the entrance examination conducted by UGC CSIR. Ms. Bhavana's research work is on the formation of brown dwarfs in nearby star clusters and variability in young stellar objects, and has published several research publications throughout her research journey. Thank you, and I call upon Ms. Bhavana Lalchand to present her work.
Hi.
Hi.
Thank you, ma'am, Dr. Leela, for inviting me. I completed my master's in Meenakshi College and not in WCC, though just a little correction. It's okay, no problem. So I would just share my screen and then start with my talk. Okay, can you see my screen?
Yes, ma'am. Yes.
Okay, thank you. So as Dr. Leela just gave a brief introduction about me, so I would be talking about formation of young luminous stars or objects in star-forming regions. I'm Bhavna Lalchand, and I'm a PhD student, final year PhD student at National Central University in Taiwan. And about myself, so this is the campus of NCU, and on this side, he is my advisor, Professor Wenping Chen, and he is one of my collaborator. And NCU, National Central University, has its own observatory in a place called Lulin in Taiwan, which is placed in central Taiwan. And the altitude of this is somewhere approximately 3,000 meters high, where we do a lot of optical survey using the telescope, and there are many other instruments with it. And on this side, this is a telescope which is in Hawaii, in a place called Mauna Kea. So Mauna Kea is a place where most of our observations are done, astronomical observations are carried out from there. So what do? I mainly work on observational astronomy, and any raw data that I get from telescope, I process it and I make it into a science quality data. So I work on various topics, one which includes brown dwarfs, how they are formed, and transient phenomena in either brown dwarfs or young stellar objects, which we call it as. And I also perform some data analysis. Along with it, these brown dwarfs and transient phenomena we look in star-forming regions. I would give a brief introduction about what star-forming regions are. And where am I? People often get misled that Taiwan is a part of China, and they think that Taiwan is in China. So this is just just to show you the map of Taiwan to show where it is. This is China, this is Taiwan, and the main capital city is Taipei, but I'm somewhere here in between. It's called as Taoyuan City. So it's a very suburban place. And this is in Taipei. This is Taipei 101, which is one of the tourist attraction in Taiwan. 101 in the sense 101 floors. So who are we? So this is my group. And as I had mentioned earlier, this is my advisor, Professor Chen Ping, and they are my group members. So myself and including this person here, Tanvi Sharma, we two are PhD students, and she is the postdoc in our group, and the rest of them are master students and undergrad students. So we work in my group, especially me and my advisor. We work quite in close collaboration with a lot of international teams, which includes, which I call it as JCMT. It is called as James Webb Maxwell Telescope, and also CFHT, which is Canada, France, Hawaii Telescope. These both are placed in Mauna Kea. So this is JCMT and this is CFHT. And in order to, when you detect some brown dwarfs or any object, any star, when you want to study their spectroscopic behavior, we usually do follow up using NASA's telescope called as IRTF, which is Infrared Telescope Facility. So again, let's just begin with observational astronomy. What are the various wavelengths that we use to study our objects? So I use the optical facility, and also some of the radio wave observable, that is the submillimeter. So submillimeter astronomy is done to study the gas and the molecular lines in surrounding the stars, because optical cannot penetrate through the dust. And then I also do infrared spectrum or infrared observing, which is in the wavelength of 100 to 1 millimeter. And in the recent launch of JWST, which is James Webb Space Telescope, infrared spectrum or infrared study is going to be even much more interesting. So what do I do? What do I study? Mainly, I study about brown dwarfs. So here I'm just going to give you a short introduction of what brown dwarfs are and how do they look like. So if you see, this is our sun. This is how Loma star, brown dwarf, Jupiter, and Earth in respect to the size order. So star is nothing but they have sufficient, they sustain sufficient hydrogen fusion. And whereas brown dwarfs, they lack hydrogen fusion because they are lower in mass. And the mass range that is used by astronomers is not very strict, but it's usually that any star that is less than 13 Jupiter mass, we consider them as brown dwarfs. So they basically they occupy a mass range between 13 to 75 to 80 Jupiter mass, and you know that planets do not have any fusion. So again, stars, they sustain hydrogen fusion. Brown dwarfs, they do not, but planets has no fusion. So how do we classify stellar classification? So in astronomy, we usually study using Hertzsprung-Russell diagram, which we call it as HR diagram. So these are the various stars in terms of their spectral type. OV, a fine girl, kiss me, L and T. And L and T, M, L and T is where the brown dwarf range of spectrum lies. And they start from very low mass stars to then they do not have enough sufficient fusion to go to be called as a main sequence dwarfs or a main sequence stars, because in order to be a main sequence in a main sequence range, you need to have sufficient hydrogen fusion. And white dwarfs, they fall in a separate they fall in separate category altogether. So our sun is a main sequence star, which is now supposed to go through a giant, then it will go through giant, and then bright giant, supergiant, and then hypergiants. So basically from giants to hypergiants, they are extremely massive stars, and it's from there that we see a supernova explosion, and then triggers new star forming generation. So as I mentioned earlier, the stars, they have mass which are greater than 0.2. So this is the limit above the stars in order to be called as a star. But brown dwarfs, they have between 0.08 to 13 Jupiter mass. So what is a Jupiter mass? It is 0.001 solar mass. And planet-based objects, they are greater than 13 Jupiter mass. So in order to, we use a lot of, we do use a lot of astronomical data, but we commonly use some Gaia data. So Gaia is a space-based telescope, which gives you accurate astrometry, sorry. And so it gives the position of very close to 20 microarcsecond for very bright stars, and 200 microarcsecond for faint stars. And it covers it has given an accurate measurement of approximately 1% of Milky Way stars in Milky Way. So in the previous slide, I just showed you the theoretical model of the HR diagram. But when you take all the data from Gaia, this is how they look like. So this is the main sequence star, and then the giant branch and the subgiant branch. So the color that you see here on the x-axis is the optical B, that is blue, minus R, that is red. So that's why those stars that move to this side, they are bluer, and move to this side are redder. So usually in our mind, the notation, when you say that the star is red, people think that it's hot, but it's just the opposite in astronomy. So red means it is cooler, and blue means it is hotter. And so how do we measure how do we measure accurate astrometry, or how do we measure accurate position? It is this way, by measuring, we call it as parallax. So this is our sun, and this is the orbit of our Earth. So for example, that we measure our position is here. We measure that this is, yes? So let's just say that this is the position of our Earth. From here, we measure a star, let's say a foreground star. And then after 6 months, when we are here, when we measure the position of that star, so the angle that you form here, the angle that you see here, is what we call it as parallax. So this is how Gaia measures the parallax distance. From where you can also then interpret it later, which I will show you how do we do that. And then in order to calculate the flux, that is the brightness of a star, how do we do is by doing photometry. So how do we do that? These are the 3 rings, which we call it as annulus. The inner one is where this object is, the object aperture. And this one is the inner annulus and outer annulus. So we subtract these 2 because these are nothing but background. So you take the mean of these 2 and then you subtract it with, so that you remove the background information from the flux. So the other curiosity that I had when I was doing before I entered into astronomy is where exactly stars are born, or where are they born? So in order for a star to be born, so we need a lot of dust and gas, and they are nothing but in the form of hydrogen molecules. So this is a very famous image, which we call it as Eagle Nebula, and this is how molecular clouds look like. And if you see in here the tips, at the tip over here, which we call it as the edge of the molecular cloud, these are nothing but the stars that are born in these molecular clouds. So these molecular clouds have a typical temperature of 10 Kelvin, which is, it has to be extremely cold. And molecular clouds, they do emit in longer wavelength, as I mentioned earlier, in millimeter or in radio. And since those radiation can pass through the interstellar medium, it is a basic, it is very perfect for us to use millimeter wavelength to study the molecular clouds, especially to find new stars. And if, let's say you want to study an optical, how does it look like? It looks like this, because any light that passes through the molecular cloud, they get absorbed. So you see a very dark patch. This is another example. This is Bernard 68. And this is how it looks like if you observe in optical wavelength. Now, below you see this is our Milky Way galaxy. So this is how it looks like in CO. So why CO? Because the hydrogen molecule are very difficult to detect. The easiest way to detect or easiest way to measure is by finding CO molecules in space. So by using CO map, you can see which in the Milky Way, where is the densest part or where exactly is the ongoing star formation going on. So star formation does not only happen in molecular clouds, but there are other places too. For example, in open clusters, which we call it as star forming regions. So where do we find open clusters? We find these open clusters in the arm of our Milky Way. And there is this other type of cluster, which we call it as globular cluster, which we find in the bulge or in the halo part of our Milky Way. So these globular clusters, they are extremely old, probably billion or giga years old, and they do not have enough gas or material to sustain the star formation. But open clusters, they have plenty amount of gas and dust to promote or to facilitate star formation. So what do I work on? So I study a region called as Perseus molecular cloud, which is approximately 300 parsec away. So parsec in the sense when you compare it to light year, so it is 3.26, something like that. So you divide 1 divided by the light year, you will get the calculation in parsec. So 300 parsec is pretty far away. And so it has a lot of ongoing star formation. And these, if you see, this is nothing but the ongoing star formation that you see here. And these are the different star forming regions. What I study on is towards the edge of this molecular cloud, that is B5 and IC348. So I have just listed what are the star forming regions that are there, but I mainly work on this and this. And so we measured, we observe IC348 and Barnard 5 using CFHT, that is Canada, France, Hawaii telescope. It is a 4-meter telescope. And using this, we identify brown dwarfs or young stellar objects. And then we use a reddening insensitive index to identify them, because brown dwarfs can often be misleaded as a background star or a reddened star because they are very faint to detect. And then after we find our candidates, we do a spectroscopic follow-up. And as I mentioned about Gaia, that Gaia gives us a very good approximation of the proper motion, that is the motion of the stars or motion of the cloud, and then also parallax. And there are other infrared telescopes. One is WISE and the other one is TUMAS. These two are ground-based telescopes. And these both are all sky survey. And Gaia EDR3 is also an all sky survey. So from these two, we identify young stellar population. So I showed you a CO map where you can map the molecular cloud of any star forming region. So this is a very small star forming region which is Barnard 5. And these are the young stellar objects, which I have marked them. So young stellar objects they also have outflows. They also have jets, which will again trigger new star forming region, because it gives you enough material. It heats up the material around, and it gives you warm dust and ionized hydrogen, which will then trigger star formation. And in these regions is we also find something called as Herbigero objects. So I have met, and these and this Bernard 5 is a very isolated dark cloud globule. So how do I find? So these are all the stars that we have observed using CFHT, and from all these stars we identify probable candidates, which I have marked here. And then we do a follow-up of these targets. And these 3 targets, I had a recent observing run, and this is how the spectrum looks like. So the spectrum is, you can assume to be a black body, and that's why you see this continuum. So this range is the wave, in this range we call it as J band or J filter, and this is H and this is K. So now recently in this star forming region, this is the first ever found brown dwarf. And how do we find young stellar objects? So as I mentioned earlier, that we use WISE and we use 2MASS to identify probable candidates. And so I used a color cut. So this is nothing but a color cut to identify young stellar objects, which we call it as class 1 and class 2. And if you see that most of the stars that are here, you can also find them in 2MASS. So if you remember earlier the Hertzsprung-Russell diagram where you saw the isochrone, this isochrone is very similar to that, but in a theoretical model. This is what we call, this is the line that you see here is where we mark them to be probable young stellar candidates. And this line is this line is the dwarf, and this line is the subgiant, and this line is another subgiant line. So most of the members that we thought to be as young stellar objects over here, which lie as class 2 objects, they turn out to be subdwarfs. And except this number 2 and 13, which lie over here, these are the Titori stars, or we call it as young stellar objects. And this one, 1, 8, and 4, which lie here, these are nothing but class 1. So the idea of doing this is that you need to, we use infrared color, which we call it as color or color magnitude, to identify such young stellar objects. So this is some of my recent publications where I have also found me and my team, which is again based in Canada. It is JCMT. So we have colleagues from Canada, from Korea, from Japan, from India, who have contributed to this in this work. So we find an extraordinary submillimeter flare. So stars, like how you see in sun, you see constant flares. We see similar flare even in stars, but finding a flare in submillimeter is extremely rare. And we have found one such flare in submillimeter. So let's talk about what are the opportunities that you can find in Taiwan. So this is a very famous institute called as Academia Sinica, and they have very good programs for PhD. So if anyone of you want to do PhD either in cosmology or in any theoretical models or observations, Academia Sinica is one of the best places to visit or even to consider for your PhD program. So they are right now starting a summer program, but for all those students who are not in Taiwan and who are from outside, they will be interacting through remote. They will be interacting remotely. It's a remote work. So if you plan to apply for the summer student program, you need to check which one of it is remote work, and then you can apply. And the other interesting opportunity is the ISYS School, International School for Young Astronomers. I attended the school in 2019, and there were a lot of students from India, especially in, I think, Nepal, Bangladesh, and I think just Nepal and Bangladesh. No one else got through. And I'm somewhere here. So it's a very interesting and a very rigorous course, but I'm sure that you will learn a lot through the school. And the other place where you can apply for PhD is National Tsinghua University, called as NTHU. They also do a variety of topics in astronomy, so you can also consider NTHU to be one of your target to pursue your PhD. And the other place where you can apply for, or you can look for PhD positions, is called as AAS. So here it is. So in this website, you would not only find faculty positions, but also graduate positions, that is PhD positions, postdoc positions, anything in astronomy. Over here, you can see anything in astronomy, you can find it here. And even I think summer programs might also be available here. So you can just go to the website and apply for it. That's all. If you have any questions, I'll take them.
The participants are requested to post your questions in the chat box. Thank you, Ms. Bhavani. The talk was very, very interesting.
Thank you. I'm sorry, I couldn't speak much because I don't have enough time to give a proper lecture of astronomy.
Not a problem, Ms. Bhavana. I'm sorry. The participants can either post their questions in the chat box, or you can raise your hand and ask a question directly to the speakers. I have Shobhana Sri Ganeshan raising her hand. Please go ahead, Shobhana.
Ma'am, I have a question.
Yeah.
Is the formation of planets possible around brown dwarf stars?
Oh, excellent question. Yes. Right now, that is what you call it as exoplanet search. So basically, nowadays people are looking for exoplanets which are in companionship with brown dwarfs. Yeah, that's an ongoing project, and my team is a part of it. It's called as Eden, EDEN. Maybe you can look it up.
Yes, ma'am. Thank you, ma'am.
Thank you. We have a question from Satish. What do you use the plasma jet for? Is it atmospheric pressure plasma jet? I'm not quite sure about the question.
Okay.
Satish, can you please elaborate on it?
The plasma jet is a completely different work. It has nothing to do with astronomy. It was just one of my invited paper. I was invited to work with the first author, Alexei Dmitriev. So plasma jet has nothing to do with astronomy. Yeah.
Satish, if in case you have any questions, please post it in the chat box. We'll ask it to the speaker later on. We have another question from Balasubramanian. He wants to know, the stars usually form in the colder region, and how the energy is released from young stars will make new star formation region.
Okay, so so you want to know how, if it is formed in cold region, then how can it form new stars?
Yes.
Okay, so so stars has its own rotation and its vibration energy. So when star rotate, it has a circumstellar disk, okay, where circumstellar disk means where there are a lot of dust. So it interacts with that dust and produces flares or jets. So that jets, when it interacts with the dust outside, it heats up that dust, and therefore it gives enough radiation pressure for new stars to be formed, enough radiation or solar wind for new stars to be formed.
Thank you, Ms. Bhavana. We have another question from Akash. How do you gather data from ground-based telescopes since the visibility of certain deep sky objects appear only a certain period of time on Earth?
Sorry, how do I what?
Gather the data from ground-based telescopes since few deep sky objects are not always visible to us.
What deep scale objects are they? I'm sorry.
Deep sky objects.
Deep sky objects, like
Yeah.
what? Sky objects like what? I don't understand.
Yeah.
So basically,
nebulas, it seems like nebulas.
okay, like nebulous. So for nebulous regions, that's why we use submillimeter. Submillimeter is a very perfect range to observe because Earth's atmosphere doesn't affect it. So it's very easy for in that range to submillimeter or radio frequency range to observe those nebulous regions. You know, because it's not affected by Earth's atmosphere.
Yeah, thank you. Participants, if you have any other question, please post it in the chat box. We'll definitely ask it to the speaker right away. I guess that is it. Thank you, Ms. Bhavana. It was our pleasure having you here.
Thank you.
We have lots of compliments for you in the chat box. Thank you very much.
Thank you.
Participants, the link for the feedback link for the session is currently up in the chat box. You can fill it up for the session. The feedback link is in the chat box right now. Participants, the link to the feedback of this session is in the chat box. You can go ahead and fill it. Ashu, the session is right now being telecasted in YouTube as well. You can go check the YouTube video later on to get the recordings. The link to the session, the feedback link for the session is currently up in the chat box. Please go ahead and fill it. The next session begins at 2 o'clock. The next session begins at 2 o'clock, and we all hope to see you back here. The feedback link for this session is right now in the chat box. We request you to kindly fill it. The next session begins at 2 o'clock, and we hope to see you all here again.
Can we have the session now? The 2 o'clock session, can we advance it?
Yes, sir. Yes, sir.
Is it possible to advance the 2 o'clock session or?
Yeah, now is it possible to use this?
Sorry?
Yeah, now is it possible, sir? Now it is okay for you, sir?
Yeah, it is okay. It's already 2 o'clock in the morning for me.
Yeah, that's what.
So,
That's what.
yeah. If it is possible, then I can
Just few
start
minutes,
now.
sir. Just few minutes. We'll be getting back to you.
Yeah, sure. Thank you.
Participants, sorry for the inconvenience. We request you to stay back. Okay, sir. Okay, yes, sir. We'll have the session in 1 hour's time. The participants can now leave for the lunch break and come back in 1 hour. We have the next session in 1 hour. This next session will begin at 1:30 p.m. IST, Indian Standard Time.
Next slide. very good afternoon to all the participants. A special greetings to Professor Satish Krishnamurthy. Thank you so much, sir, for having joined us now here, the post-lunch session in India, and early morning greetings to you there abroad. Dr. Satish Krishnamurthy is a very vibrant researcher, very young, and his resume will be read by Dr. Rajeshwari shortly. We will understand that so much of accomplishments at this young age is really astounding. We were just discussing with the staff members. It is such a pleasure and privilege to have you with us today, this afternoon. Thank you so much, sir, for joining us, sharing your precious time with us. Now I hand over the session to Dr. Rajeshwari to introduce our esteemed speaker, the participants, and a wonderful listening to all of us from Dr. Satish. Thank you so much.
Good afternoon and a warm welcome to the post-lunch session of our workshop. It's my privilege to introduce Professor Satish Krishnamurthy, Professor and Chair of Energy Technology, School of Engineering and Innovation, the Open University, Milton Keynes, UK. Professor Krishnamurthy is a Fellow of the Royal Society of Chemistry, Fellow of Materials, Minerals and Mining, Vice President of the Indian Chamber of Youth Entrepreneurs, and an honorary faculty of the SRM Institute of Science and Technology. An alumnus of the University of Madras at the postgraduate level, Professor Krishnamurthy received his PhD degree from the University of Newcastle upon Tyne in 2004. His research focused on silicon quantum dots, carbon nanotubes, and carbon onions. His path-breaking work during his PhD on gold nitride was patented and was broadcast on a special issue on BBC. As a research fellow at the Trinity College, Dublin, from 2004 to 8, Professor Krishnamurthy continued his research work on noble metal nitrides and their synchrotron-based spectroscopic investigation and identifying origin of ferromagnetism in TM-doped ZNO. From 2008 to 12, as research fellow on thin film deposition, material and surface scientist at Dublin City University, his work focused on renewable energy and biomedical implants. As a recognition of Professor Krishnamurthy's commitment for socially oriented research, he was invited by former President Dr. APJ Abdul Kalam in 2007 to discuss the social impacts of nano initiatives in the Indian scenario. He has since then headed several delegations to forge tangible scientific and innovative partnerships with India, representing Ireland in the EU-India Research and Innovation Forum. As professor and chair of energy technology at the Open University, Professor Krishnamurthy's research group is involved in the research of advanced functionalization nanomaterials for alternate energy, energy generation and storage. With more than 70 international high-impact publications, 2 international patents, and 2 more on the anvil, to his credit, Professor Krishnamurthy is an esteemed member of the Royal Academy of Engineering, UNESCO, and various other research councils, and the peer reviewer of several high-impact factor journals. His projects, having valuable impacts on society, have been funded with research grants by major research councils like Erasmus+, Royal Society, Royal Academy of Engineering, etc. Some of his completed and ongoing projects include development of an open access remote photovoltaic laboratory, graphene assisted low cost energy efficient solar cells, smart innovative system for recycling wastewater, plasma functionalization of low-cost flexible solar cells, and climate-compatible growth. It is indeed an honor to have Professor Krishnamurthy share his expertise with us today. A warm welcome to you, sir. Over to you, sir.
Yeah, good morning, everyone. Good afternoon. I hope you can hear me. It's 3 o'clock in the morning here in UK. I'm not in UK, actually. I'm in Colombia on a business trip. So without any I'm just quickly sharing my research findings and motivation for the research. I hope you can see my screen.
Not yet, sir.
Yes.
Yes,
Yeah.
sir. It's visible now.
You can see my screen, right?
Yes, yes.
Yeah, thank you. So thanks for the introduction to the introduction given by the chair. And I work on different areas of research with water, energy, and food nexus. So I feel that all the three are linked together in order to have a sustainability of the research. So I just wanted to give a brief overview of this research, particularly on energy security, water security, and food, and how materials will make a bigger impact on this. Before that, I'll just tell what is Open University is one of the largest university in the world. I think it's about 200,000 students we teach each year, and we are pioneer in distance education. With we are running quite a lot of remote labs, and also there are about like 20 robots or cut the engine and then slice and analyze the different engineering concepts. And also we have a remote SEM as well, where we can, any part of the world, people can see the microscopy at the nanometer scale by sitting in their, we bring the lab to the desk. So there are quite a lot of innovative concepts which we have brought, and that has given us the platform to reach the millions. On top of that, we have several education platforms with which working with India on Test India project, MOOC, Test MOOC, and then the girls' access to education. So this is on the education bit which we are doing, and educating the people on societal needs, exactly on the outreach issues. Right. So in this talk, I will focus on sustainable development goals. So how research should effectively address the stakeholders. The stakeholders are us in terms of the public, and how it can give a poverty, zero poverty, zero hunger, good health, quality education, gender equality, clean health, clean water and sanitation, affordable energy. So there are quite a lot of sustainable development goals are there. So my research will be focusing on 3 of such sustainable goals. One is good health, quality education, clean water sanitation, and affordable and clean energy. So why do we need to restore our planet? There are 3 points which I would like to focus on: biodiversity loss, climate disruption, and escalating pollution. As you can see, the major challenges needs to undo is cut forest and the polluted rivers. And these are all like real pictures. There's no editing or anything there. And similarly, if you go to the cloud where the vegetations are also under a huge risk because of lots of what do you call, the 40% of the world population lives in food insecurity because lots of chemicals being introduced that is killing the fertility of the land. So how we can use natural
Sir,
chemicals.
your slides are not moving, sir.
I don't know. Am I sharing the correct one?
Now it's like 10th slide, sir.
Yeah, 10th slide. Okay.
It was not moving.
Okay. I'll leave it like this so that I don't know why in the slideshow it is moving. Okay.
Okay, just leave it like that.
Yeah. So we're talking about. I'll make it slightly bigger.
Slideshow.
Okay. So we are ravaging our ecosystem that is underpinning the society because of the food and water we have. So we still have time to revive the damage. For this, there are quite a lot of government, civil society, industry, and citizenship have all talked together in order to address these bigger challenges. Some key facts is the forest serves as a natural resource for carbon. We are all talking about carbon dioxide capture, and there's a huge COP26 meeting happened here. COP26 is a climate action program, and that is talking about high level how we need to secure the biodiversity, and also all the food, energy, and water, which I have been talking about it. So it's a huge program. Even India has a Clean Up Ganga project is there. Science tells us the next decade is crucial for us to undo the catastrophe and turn back into that tide by especially the losses. So if I go back, this is the bigger problem we need to address. We cannot address it just only by one research group or two research groups. So I'm working with a consortium of much bigger international research agenda. And one of the major thing vision is socially oriented research that has direct benefit to society. So we work on surface engineering of materials, manufacturing of functional materials for energy storages and solar harvesting, 3D printing of plasma-based processes, coatings. There are quite a lot of interesting things which we are working on. As I mentioned in my previous talk, is these 3 sustainable development goals which we are working. So all our projects are currently funded by different funding agencies, European Commission, Erasmus Plus, Royal Society, and Newton Fund. So these are all, without them we cannot do research. So we do quite a lot of things. And in terms of ongoing funded projects, I'm currently on my waste to fresh as a wastewater treatment project. It's a 8.5 million pounds. It's a consortium of about 17 people working together on a platform to clean water and recycling of batteries. Another areas which we are working, because there are more batteries than human beings. As you know that there are more cell phones than human beings in this flat. So if you have more cell phones, more batteries are there. So it keeps building. So, and then different types of work with Tata Steel, etc. So you can go to my webpage, you can see that. And in terms of our research expertise, we work on metal nitrides, oxides, nanotube, different types of nanomaterials, solar cells, and also spectroscopy to address the challenges of the industries. These are all the industries which we collaborate, including Bank of England. So one of the there are 4 projects which I thought that I might share one of them. So one on industry wastewater treatment with this one, the Royal Academy of Engineering in partnership with the PSG College of Technology in Coimbatore. And there is a Newton Fund which is batteries and another battery projects, and this is for solar cells, and it's a bigger project on wastewater treatment. And this one is a real picture coming from Bangladesh. The dye, if you see, this is the textile industry, and the dye goes here. See, so these dyes are carcinogenic. How science can feel this water problem? So we started thinking of challenging this problem by 2 ways. One is biotechnologies using aerobic and anaerobic bioremediation, and material scientists like us who can produce low-cost catalysis to treat the water on the scale of things. So to any ideas has to come from brainstorm. So we conducted especially focused conferences on inviting the industries from India, industries from UK, and then we had like a two-day conference, one in India and one in UK, to understand the challenges. Once we understood these challenges, you can see this textile industry consumes about 140 liters of water per kg of finished product, and similarly the energy is equivalent. So we thought that how we can do this by going into new technologies. And if we look at the history of water, water problem is there for ages, right from ancient drinking water of boiling it in charcoal, 4000 BCs, to all the way to agriculture sectors, and then the Egyptians used different types of alum. So that water problem is there for plenty of years, but it has grown in subsequently these days. And now we are talking about one of the worst technologies, reverse osmosis, and it takes out all the minerals and then it just gives the water without nothing. And this is not good for health. So how we can address this issues in a global scenario? Let us focus on water and sun. So sun is the source of energy, and then how we use renewable energy from the sun, and also to treat the wastewater. So we use photocatalysis. Photo is light, and catalytic degradation. We use catalytic degradation to purify this water. Different types of materials which we use. As you know that graphene is a two-dimensional material. The two-dimensional material is nothing but it forms a thin layer of sheet and has only is plane of directions along the two corners. And graphene is like a slice of, if you take a pencil or lead, and then if you put this into a microscope, you see like a dosa or a pancake. And if you slice the cross section of a dosa, like what do you call paper roast, you call that is itself is graphene. If you take the graphite and take a slice and thin layer, and similarly from that there is plenty of two-dimensional materials originated like molybdenum sulfide. You can make maxine. So generations, or then you can tune it. So my group is working on different types of materials which we use for photocatalysis, batteries, and sensors. So why 2D materials? These dots have a significant affection due to a large area of different morphologies, broad band gap, strong absorption. So we can tune, and depending on how many layers you can split, you can tune the band gap. And also you can functionalize these materials to have a more active site. So that's a very super advantages of these materials. And if they do go into the transition metal chalcogenides like Mars 2, it's very important. This has a good light harvesting things are there. So currently we are using a photocatalysis. It is like we make the catalyst and shine light on that, and then forms an excitonic pair. Excitonic is like electron hole pair it forms at that particular wavelength. And in that particular wavelength, we have attached the metal catalyst, metal co-catalyst, so that we are using the surface plasma resonance to induce on that, and we make a functionalized particle so that we have a photo-induced hydrolysis for hydrogen generation, organic photocatalysis for degradation of pollutants, and then the synthesis of organic compounds. So once we did this, then you see this is a titania. Titania is like it's pretty much used in everywhere, including our food, and also the fillings of our tooth. The titania is part and parcel of our brain, so it's an earth abundant system, so that it can easily be commercially scalable. So we use the titania and then treat it with hydrogen and also with graphene, and then we can clearly see the difference between them. Optically, you can see. When you see optically, means it through your eyes, you can see the difference. Then definitely the penetration of the light will be different as well, and the electron hole pair combination.
Sir, can you please unmute yourself, sir?
Mouse இல்ல காத்துல கூட இந்த இது ஆஃப் ஆயிரும்.
When you stopped listening to me,
just now, sir.
Somebody has unmuted me then. Okay. I don't know where I stopped.
Now you get the same slide only, sir.
இல்ல இல்ல எப்போ ஸ்டாப் ஆச்சு?
Like or 10 seconds தான் sir ஆச்சு.
Okay, okay, that's fine. Yeah. So we functionalize this using hydrogenated TiO2. அதில் பார்த்தீங்கன்னா you get a different when you see things optical changes here. Then we put optical spectrometer la potona, then you can clearly see what you see in the eye is what you see in the spectrometer. So you can clearly see this is an absorption. Absorption is and the light உள்ள போன உடனே அதோட இழுத்துக்கிற தன்மை that depends on the electron hole pair combination. அப்போ வந்து என்ன ஆகும்னா உங்களுக்கு வந்து அப்சார்பன்ஸ் இன்னும் கொஞ்சம் ஜாஸ்தியாகும். அதுதான் எக்ஸாக்ட்லி இங்கே நடக்குது. நீங்க பார்த்தீங்கன்னா அந்த டெய்ல this absorption is higher. So this absorption will go and trap the electron hole pair much longer time. Then you are getting a better activity for the catalysis. And how it is produced, you can clearly see one TEM on a transmission electron microscope. So if I have time, I can give you a tour of this kit, which I will do that quickly towards the end. And இதுல வந்து எப்படின்னா I will just make the zoom it up slightly bigger. Yeah. So here, this is taken in our lab. இது வந்து லாட்டிஸ் ஸ்பேசிங் நம்ம ஊர்லலாம் வந்து எக்ஸாலஜிலாம் படிப்பாங்கன்னா இங்கே எக்ஸ்ரே ரெஃப்ராக்ஷன்லாம் அப்போ எக்ஸ்ரே ரெஃப்ராக்ஷன் பீக்லாம் வரும் வந்து அதை வச்சு நீங்கள் வந்து லாட்டிஸ் ஸ்பேசிங் அதெல்லாம் பண்ணுவீங்க. இட் இஸ் பிரிட்டி மச் தட்ஸ் வாட் வி ஆர் டூயிங் ஹியர். In this we are doing this lattice spacing of the fringe and இதை மெஷர் பண்ணிட்டு you can see there is a difference between here and the here and the here. So we are forming it composites. Okay, composites, and that composites it's important for activation of the catalyst. Then அதுக்கப்புறம் வந்து we do X-ray photoelectron spectroscopy. This X-ray photoelectron spectroscopy it will give you the information on the chemical bonds. So once we functionalize this, what are all the chemical bonds present in the sample? So that chemical bonds is the one which is responsible for different activities and also electron transport and hole transport phenomena enhancement of output. So that is what we are trying to find here. And once we do that thing, we need to scale up. So we developed an in-house plasma printer. Print பண்ணும்போது we have an ink மாதிரி ஒரு எடுத்துக்கிறோம். So we made this titanium composites or molybdenum composites or even graphene composites. அதை எடுத்துட்டு ஒரு ink, we form an ink பண்ணிட்டு then this is what we do. Let me see if it works. Now we can print out the composite. As you can see, this is a plasma. Okay, in the plasma on the atmospheric jet plasma. Probably the previous speaker was talking about some review of the wrote on atmospheric jet plasma or review application. Even on the atmospheric jet plasma, we are printing this onto the silicon. In this case, silicon what it becomes substrate. So once it's printed, it is scalable for high manufacturing. Okay. And it has two electrodes phenomena. Once we prepare this, then we can see that catalysis is happening. இதெல்லாம் வந்து solar light, simulated light. You can see that we are cleaning the water. This is water, dirty water, and we are cleaning it. And these bubbles are nothing but the reactants, organic reactants in the water is getting reacted, and then that is carboxylic acids and CO2 release we convert on hydrogen, and the hydrogen these are nothing but hydrogen bubbles. So அதை வந்து different types of nanoparticles which திருப்பி கோட் பண்ணி fine tune பண்ணிட்டு இருக்கோம் நாங்கள். Then we are using different materials. MOS2 molybdenum sulfide, அதை வச்சு how we can enhance the properties. So So then we can clearly see that we can control the lattice spacing with the TiO2 and MAS2 composites. Other two health phenomena வச்சுட்டு then we are finding the XPS நான் சொன்னேன்னா X-ray photoelectron spectroscopy that gives a fingerprint of what is happening at the chemical at the surfaces. So we try to understand, as you can clearly see from the red to the black curve, there's a shift is happening. This shift is nothing but tuning of the electronic properties of the system. And we are able to tune it where we wanted to increase the absorption, and similarly the X-ray diffraction in Raman is also gives the required changes what we wanted. Okay, then we started thinking how we can use a combination of increasing the molybdenum sulfide concentration to TiO2 to fine-tune the property. So, 2.5% gives a better photocatalytic property, 50% absorption. So we use a combination of higher molybdenum sulfide, that is thin two-dimensional sheets attached to the surface, to the lower molybdenum. The lower and now transmission is more, and transmission is more, and sort of high catalytic activity. But 50% and thicker, more layers, so absorption is more. So we use a combination of batch processing. It is given we can clean the dice in about 5 minutes. We clearly clean the dice with a very less energy of solar. So as you can clearly see that if you see the traditional dice takes about in about 15 minutes we completely clean the die with a visible light, which is a fantastic results. Then we started looking at different combinations, etc., how to do this, and different stages from different dyes, crystal violet, methylene blue. இதெல்லாம் வந்து நம்மளோட from head to toe we are contaminated. We are talking about contaminated outside. We are contaminated because we are all as the different dyes. It's made up of, and how to clean that. And then I will show you some examples of those projects which I wanted to. So these are all like using a solar cells. We have a solar cell, and then in this solar cells, which we homemade solar cells, which we did, and with this solar cells, we put the new dyes. Denim blue. Denim blue is nothing but the trousers which we have, the stone wash jeans and other jeans. So we work with those jeans that comes with the effluents, and that is the effluents which you see in the right. We use our catalytic material to clean the water, and we take out this water out, and then try to understand what is inside this water, and using our electrocatalysis phenomena. And we also do another thing which is on seawater. So we end up on in the catalysis seawater about so seawater, how it treats with seawater. As you can see, that is a magnetic thing, stirrer, and we have a very simple, very simple tool. Some material is coated, which I can't say what it is, and very simple plastic mesh. With this mesh, you can see that what is happening here is the solar cells is here. It is given by solar cell, not with any other thing. It is given by solar cell, and you can clearly see the bubble coming out from the surface. There is a hydrogen production that is pretty much like this. So this is a very simple phenomena, 100% renewable energy, and we are getting hydrogen out of wastewater. This is a fantastic concept which we developed. And similarly, if I go to the lab experiments, we have another plasma. It is a plasma. It's coated onto the copper, and we can see this. It cleans the water in about 10 minutes to 20 minutes and 30 minutes. You get a very clean water using our technology. Then we decided that how we can work together with in installing this in a commercially bigger scale. Tirupurla or plantla, we have worked with the plant with combination of vetiver. Vetiver is a biocomposite, and we coated our material onto the vetiver and put it inside the tank to clean the water. And then it worked really well, and we have a sensor as well on this. So it is a very successful project which we implemented. And how we do this is like the traditional process is this, using a physical separation, chemical, biological treatment, RO, and barren concentrator அப்புறம் பாண்ட்ல போட்டு evaporate பண்ணிடுவாங்க. So it is very complicated traditional cleaning process. It involves lots of money involved in it. And the money is involved, people tend to not to spend more money on this, considering different situations. So here we have gone into how photocatalysis can reduce the money and also increase the uh, increase water treatment. So other one is the replace பண்ணிட்டு we put a catalytic system, and there is also another replacement which we did. All we thought is how we can use natural fibers. The natural fibers which is cellulose, நம்மோட தேங்காய் நார் இருக்குல்ல அந்த மாதிரி how we can extract that natural fibers and put new materials in it to clean the dyes. It's pretty much like this biocomposites. And we use different multiple sensor technologies using these biocomposites to detect water, and also we use it for anti-fouling coatings. Thanks to all our funders, then to my group as well, who have been doing this. Now it is expanded. இதை கொஞ்சம் நான் வந்து I'll stop the screen share and then I'll share another one to show the what facilities we have. I think so we have in our group, we have magnetron sputtering. So this sputtering is a DC sputtering we have, and also pulse DC sputtering. So we have a target cathode. Targeting what do you call என்ன மெட்டீரியல் பண்ணுறோங்கிறது டெபாசிட் பண்ணுறதுக்கு என்ன பண்ணுவாங்கன்னா we mix all the material and then பெல்லட்டை பவுடரை வந்து பெல்லட் ஆக்கிட்டு அந்த பெல்லட்டை வந்து we attach onto the substrate, onto the holder. And the holder பண்ண உடனே then we pass electric current on this, and then it will at the specific energies 13.66 megahertz frequency, particles will try to come out of the surface, bounce back each other because of the see, generally when you heat the surface, your heating is happening upon the entropy increases. Entropy increases, vibrations, so we started vibrating the atoms. We have a heat, and then with this heat, these atoms will be ejected at the particular energy, and the position takes place. So we know magnetron sputtering that. So in the then after that we have different types of plasma reactors. So அது வந்து நாங்கள் இந்த பிளாஸ்மா ரியாக்டர்ஸ் பிளாஸ்மா ஜெட் டெபாசிஷன் வாங்க. இதில் பார்த்தீங்கன்னா இது கிளாஸ் லைட்ஸ் லைக் திஸ் 2 slides, and then we pass gas in it, and it works with the atmosphere. The atmosphere வந்து ஆக்சிஜன் அண்ட் நைட்ரஜன் இருக்கும். அதை வச்சு இது இப்படியே சர்க்குலேட் ஆகிட்டு இதுக்கு வந்து பிளாஸ்மா ப்ரொடியூஸ் பண்ணுவோம். இட்ஸ் கால்ட் ஜெட் பிளாஸ்மா மெத்தட். see all in our group pages. இது நாங்கள் நல்லா பண்ணதுனால டாடா ஸ்டீல் இஸ் டொனேட்டிங் அஸ் திஸ் அட்மாஸ்பியரிக் ப்ரெஷர் பிளாஸ்மா கிட். ஓகே, திஸ் அட்மாஸ்பியரிக் ப்ரெஷர் பிளாஸ்மா கிட்டில் வந்து ரோல் டு ரோல் நீங்கள் பார்த்தீங்கன்னா ரோல் இருக்கா, 2 ரோல் இருக்கா, இந்த பிரிண்டர் பேப்பர் பிரிண்ட் பண்ணுற மாதிரிலாம் இருக்கும். திஸ் ரோலர் யூ கோ put your paper, அதே மாதிரி நீங்கள் வந்து சப்ஸ்ட்ரேட்ஸை போட்டோம்னா you can print anything or anything, any 2D materials or any material on this to accelerate the production. அது பண்ணிட்டு தென் ஒன்ஸ் பண்ணிட்டீங்கன்னா நீங்கள் வந்து எக்ஸ்பிஎஸ்னு ஒரு கிட் இருக்கு. இதில் வந்து அனலைசர், திஸ் அனலைசர் இஸ் அனலைசிங் எலக்ட்ரான்ஸ் கம்மிங் அவுட் ஆஃப் த சர்ஃபேஸ். இந்த சேம்பர், இந்த பண்ண சாம்பிளில் வந்து இந்த சேம்பரில் போட்டு கெமிக்கல் அனாலிசிஸ் பண்ணலாம். ஓகே, and then we also have electrochemistry facility where we வந்து எப்படின்னா கெமிக்கல் ரியாக்ஷன்ஸ்லாம் நாங்கள் இருக்கோம். ஸோ பர்டிகுலர் கரண்ட்ல ஸ்விங் பண்ணோம்னா எப்படி ஆக்டிவிட்டி சேஞ்ச் ஆகுது அண்ட் ஹவு வி கேன் கெட் மேக்ஸிமம் எஃபிஷியன்சி அட் பர்டிகுலர் அயனைசேஷன் பொட்டன்ஷியல், அதை வந்து நாங்கள் இந்த இதில் பண்ணி பார்ப்போம். தென் we also have battery tester and also a solar simulator. Solar simulator வந்து it mimics the sun. And we also have atomic force microscopy and also electron microscopy. இது வந்து எங்கள் குரூப்பில் இருக்கிற இதுங்க ஸ்கேனிங் எலக்ட்ரான் மைக்ரோஸ்கோப். அதில் வந்து யூ கேன் ஆல்சோ சி இண்டிவிஜுவல் லேயர்ஸ். இது வந்து ஆக்சுவலாக அது வந்து பிக் ஷீட்ஸ். இது இன்னும் நாங்கள் ப்ரோவ் பண்ணோம்னா யூ கேன் கெட் சம்திங் லைக் திஸ். ஓகே, லைக் திஸ் வேர் யூ கேன் எஃபெக்டிவ்லி சி ஆட்டம் பை ஆட்டம். அந்த மாதிரி நாங்கள் பண்ணிட்டு இருக்கோம் தான் டிரான்ஸ்மிஷன் எலக்ட்ரான் மைக்ரோஸ்கோப்பில். Okay, I think with this, I will stop. I think it's a kind of a quick whistle stop show. Usually I spend more time, but I'm spending slightly lesser time today. And thank you so much for the opportunity and open for any questions.
Thank you, sir. The session was very wonderful. And I ask participants, can you, if you have any questions, you can post in the chat box or you can either raise your hand.
Sir, thank you, sir. Your talk was wonderful talk, sir. Thank you so much, sir.
Looks like that I haven't excited much people because of it's about 3:30 in the morning here, so energy level of mine is a bit low. So sorry about that.
But your session was wonderful, sir. We actually learned a lot about the wastewater treatment and like how your project, how you have implemented so much of project in your through you. So actually, so we enjoyed this session, sir. So I thank you again, sir.
Okay, thank you so much, sir.
So thank you, sir. This is Dr. Mahalakshmi, sir. Sorry, we have disturbed you in the middle, sir, in the middle of your sleep.
No problem. No problem.
Thank you so much, sir.
Participants, the feedback link has been given in the chat box. Kindly fill in the feedback link and we shall start our next session in a few minutes.
Good evening, everyone. I take immense pleasure in introducing Dr. Sanveer to this gathering. I would also like to express my gratitude for agreeing to give a presentation at this workshop. Dr. Samuel earned his MSc from the American College, Madurai, and then he moved on to Anna University for his PhD. He completed his postdoctoral studies from the University of Central Florida in the USA, and then he was a researcher at University of Rovira at Gilly, Spain, and from 2016 he was a senior researcher at Highlands Research Center. Currently, he is a scientist at Highlands Research Center in Czech Republic. Dr. Samuel has been the recipient of various awards and fellowships such as Japanese Government Scholarship by Government of India and Junior Research Fellowship at VRNS Project, etc. He has published 25 peer-reviewed research articles internationally and 2 at the national level, traveled to over 14 countries, and presented over 30 conferences. He also serves as a reviewer for a number of international research grounds, and he was an editorial board member of the Non-Metallic Materials Scientific Journal. Dr. Samuel has also authored 8 chapters on material science and ceramics. His research interests include diode pumped solid-state lasers, laser crystals, transparent ceramics, cryogenic lasers, and spectroscopy. In addition, he is one of the best physics and scientific promoters on the internet with his YouTube channel named Science with Sam, Arrivial Arivu. I'm extremely pleased and delighted to introduce Dr. Samuel as the speaker for this session. I would like to extend a warm welcome to Dr. Samuel to deliver this presentation. Thank you, Sam.
Can you see my screen?
Yeah, sir.
Good afternoon, everyone. So I am Samuel. First of all, I thank the management of the Ethiraj College for Women, Chennai, for inviting me for this workshop. It's a privilege and honor to be a participant and presenting the topic in advanced materials for solid-state lasers. I also thank Dr. Kavita, my friend and my master's classmate at the American College, for considering me and requesting me to be a part of this workshop. I'm happy to be connecting with students and faculty members at Chennai. Unfortunately, my talk is preponed by an hour. So it is 10 o'clock in European time. So I just came to office and I am joining the lecture. So today I will be presenting the topic, as I mentioned, advanced materials for solid-state lasers. You can connect me at my official ID. Otherwise, as Dr. Kavita mentioned, you can also reach me at my YouTube channel, Science with Sam. It's a pretty recent channel and which is attracting a lot of young science-interested people in Tamil. So you can enjoy more scientific topics at this YouTube channel. So currently I'm sitting here like almost 7,100 kilometers from Chennai. I am in the country called Czech Republic. Many of you may have heard. Always people think it's like a Czechoslovakia. But Czechoslovakia is split into 2 countries. It is Czech Republic and Slovakian Republic. So I am in the capital of Czech Republic. And people are talking about Ukraine today because of the war with Russia or something like that. So Ukraine is not very far, but also we are not very close. So we are still safe. So I can give a talk without a war, I think, because they're expecting war anytime soon. So I'm in the capital. It's a very beautiful city. If you happen to be visiting Europe, you should visit Prague as one of the places to visit. It's a pretty old city. I'm from Madurai originally, so I'm already from a very old city. And still, this city is quite beautiful. So it's a very red rooftop buildings. This bridge is like 600 years old bridge. It's a very historical city. You should consider visiting if you happen to be near. So the Prague is a different climatic conditions. This is winter, this is autumn, and this is like summer, and this is at night. So Prague is beautiful all through the year. I love being in this city. I have been living here for more than 5.5 years, and I enjoy almost every day in this city. And Prague is not just a touristic spot, it's also connected with a lot of scientists. The historical connection with science goes long back. Tycho Brahe, you may have heard of his as an astronomer. He was like a boss of Kepler. So a lot of people have heard about Kepler, but Kepler was taken to Prague by Brahe. So they both were astronomers, and you physics students may have heard, like they made immense contribution for astronomy. And then like very less known member, Marcus Marcy, and he was one of the guy who mentioned about dispersion even before Newton. So Newton is connected to the dispersion of colors, white colors, but even Marcus Marcy from Prague even described.
Sir,
Is there any problem?
sir, sorry to interrupt you. Participants are
Yes.
saying that your screen is not visible to them.
Your video is
Your video is not.
Your video is visible, but your screen, are you shared any screen?
Yes, I
PPT.
shared my screen.
PPT, we didn't see.
I'm sorry. Can I stop and?
Yes, sir.
Now can you see?
No, sir.
Your video is there, but your screen shared is not. It's coming.
Now it's yes, sir.
It is saying someone else is presenting. I think somebody is blocking my screen for some reason. Can you hear me?
Yes, sir. Yes, sir.
It is saying that somebody else is also presenting. So I think it's somehow, I think it's overlapping.
Okay.
So when did you miss, so at least did you watch these pictures?
No, sir.
Oh, right from the beginning? Oh, I'm sorry. So I had to start from the beginning. So now you can see the first slide.
Yes, sir.
Okay, at least you heard my voice. So I will just skip quickly. So if you want to contact me, you can contact at my official ID, and you can also connect with my YouTube channel. So I am from the city called Prague, so which is like, as I mentioned, it's like 7,100 kilometers from Chennai. So this is the Central Europe they call. So this is like the Western Europe, which is richer countries like Germany, France, Italy, Switzerland, all these Western countries, and they call the Eastern countries like Poland, Ukraine, Belarus, Hungary. All these things are Eastern countries, and we are in the Central Europe. So was attacked by Hitler. Czech was attacked by Russia. So even now, Czech is having a problem with Ukraine. So as I mentioned before, so it's still a beautiful city. As I mentioned before, if you have a chance to visit, consider Prague is in your list. So this is yeah. I'm sorry. I think the organizers should stop people. Can you watch my screen?
Yes, sir. Yes, sir. Your screen is visible.
Because I see a lot of people are talking in between, and I'm just confused. Okay. Anyway. So this is connected with scientists. So as I mentioned, Brahe, Kepler, and Marcy, and Doppler is famous name. He worked in the physics department, mathematics department in physics, also in physics in Prague, and then Mach principle. They know the Mach speed. This is related with Mach, and he also lived in Prague. And not least, the great Albert Einstein. He was working as a professor for more than a year in Prague, and during this time, he mentioned that he got the necessary concentration to work on the general theory of relativity in Prague. So he invented this special theory, and he took almost 10 years to invent this general theory of relativity. So one of the period of time he worked in Prague for over a year. So if you walk along Prague, you always come across some of the places where these great scientists lived. They stayed, they played music, they took food, they walked the street. So it's an amazing place that you can experience such kind of eminent scientists living place in the city. So I am from the city, from this center called HILACE. So HILACE is a short form of high power laser. So it's actually called a high average power laser. So this is like a short form of this high average power laser. That is why it's called HILACE. The building is like a ship. So yeah, this is my boss design, I think. So this is one of the biggest lasers. Sorry. Okay, anyway, so I want to talk about this particular laser, which recently achieved a world record. So the world record laser is 145 joule in 10 hertz. That means in 1 second, you have 10 pulses, like that. 10 pulses in 1 second, and each pulse is 145 joule. This is a huge energy, and that's why it has got the world record. This is the 4th world record this particular laser has achieved. So basically, this is the laser that I want to talk. But I want to talk exactly the material that made this laser to achieve this world record. So I'm not going to talk in detail about the laser system. Maybe some other day, if I have a chance, I can talk about the pure laser. I want to talk in which made them to achieve this particular energy. And this is the advantage of the advanced materials. Thanks to the advanced material that this was possible by these lasers. So this is like the Guinness World Record. So this is in our office, just to be sure that I did not directly work with this laser. I wrote a review article on this laser, but I did not directly work on this laser because this laser is dedicated only by the local people. So mostly the people working here are the Czech people. So this is the Guinness World Record, and some of the record parameters are each pulse is 146.5 joule, and the pulse width is 10 nanosecond. And the repetition rate is 10 hertz. That's what I was talking about. Like in 1 second, you get 10 pulses of this energy, and the wavelength is 1030 nanometer. And then the average power. So this is like 1.46 kilowatt. That is why this is called a high average power laser. That is why our institute is called HILACE. So this is one of the reasons. This is the average power laser, the world record. And a lot of people may have heard, whoever has studied the lasers, they may have known about the most powerful laser in the world is like National Ignition Facility in Lawrence Livermore Lab in the US. So they have an energy of 21,50,000 joule.
Excuse me, sir. Sorry to interrupt. There seems to be a technical glitch. Your presentation and your mic is muted.
Presentation also closed.
You're still muted, sir.
Okay, can you hear me now?
Yes, yes. And your presentation is gone. So we'd like you to reshare it.
Can you see it now?
Yes, sir. It's there. Yes.
So which slide you missed? This slide you saw?
Uh, no, we haven't seen this one.
This one?
Yeah, we saw this.
Okay. So can you please stop me immediately if you miss my screen?
Sure, sir. Yes, yes.
Okay, I'm so sorry that there is some problem. I don't know. But I think somehow the Google is blocking when somebody is interrupting, I think. Anyway.
Yes.
So
Please go
now you
ahead.
see my screen. Okay.
Yes.
So yeah, people are always talking about the highest energy laser as the one in the US, but yeah, there is a different powers that we are talking about. So I will, so this is the laser that we have it here. This is like 15 meters long. So they call it as a compact laser. One of the reasons this is called as a compact laser is because some of the lasers like the size of a cricket stadium. So you can imagine the laser of the size of a huge hall or an auditorium. Compared to this laser is very compact. So this is still 15 meters long and 5 meters wide. So this is pretty long laser. So this is how it works actually. So you start with very low energy. The energy starts with nanojoule. Then you amplify to 5 millijoule. Then you amplify to 100 millijoule. Then you amplify to 10 joule. Then you amplify to 100 joule. And recently the record reaches like 145 joule. So in these two places, the 10 joule and 100 joule, they are using some advanced material, which is like a transparent ceramics, which is very remarkable material in lasers. So this transparent ceramic played a major role to achieve this 10 joule and 100 joule energy. So I want to show the video, how the laser looks, so that you can have an idea how the laser looks like 15 meters long, this huge laser. I have compressed the video as like 3-minute video, but this is like more than 15 minutes. I have also uploaded the video with complete details in my YouTube channel. You can check it. I will just share the video.
I'm sorry to interrupt you again. The slides are
stopped?
not changing. Yeah, it changed right now.
Now it's changed?
No, it's still in the video slide. Let's watch the video slide. Slide number 11.
Yes.
The video is not playing, but we still
Yeah.
have.
I will share the video now.
Mhm.
So you can see the video now.
You haven't shared your screen yet, sir. One second. Yes. Now it's playing. Yes.
So this is the laser. So this is like a huge components. These are some cooling systems. So this is like 15 meters long, and this is like 5 meters wide. So this is like taller than me. I'm almost 6 feet, and this is even taller than me actually. So basically, the laser starts from this small box. So I will just. So you can also hear me, right?
Yes, sir.
Okay, so basically the laser starts from here. So this is like the nanojoule I was talking about. Like this is like a fiber laser. So this nanojoule is very weak. This is a fiber oscillator, and this nanojoule comes to the red box. So when this nanojoule energy from here, it's amplified to millijoule. So as I mentioned, the nanojoule becomes millijoule. This is like 5 millijoule. So here there is a crystal. This is like calcium fluoride. This is ytterbium calcium fluoride, and this 5 millijoule laser goes to this white box. So there are some shaping, they change the shape of the beam, they adjust the temporal pulse, they change the frequency. So the frequency is changed from kilohertz to 10 hertz. So then this laser goes to this white box. So this white box amplifies the laser to 100 millijoule. So first nanojoule, then 5 millijoule, then 100 millijoule. So this is from Astronomy, this is from German company. So this is also has another crystal. This is like ytterbium yak. And so this amplified pulse is again shaped. So they get some square pulses. So there is some beam expander. So here they can manipulate the size of the beam. And this beam is going again. This 100 millijoule beam goes into the tube, and this goes inside the chamber. And here it's amplified to 10 joule. So this is where the advanced material, this is where the transparent ceramic is located. Of course, now it's completely covered. Why? Because this is cooled from liquid helium. So the helium flows from the top. So this is extremely cold, actually. Actually, the laser is running right now. But I muted my mobile phone. I was recording in my mobile phone. And this beam is again going, like this 10 joule beam is going further. And then it comes for the other amplifications. This is what they call main amplifier. So this is the cooling system. The liquid helium is flowing from the top. And here they have another set of transparent ceramic. So in this case, the 10 joule becomes 100 joule. So basically the world record was achieved by this transparent ceramics in this main amplifier. So they call it as a pre-main amplifier, and they call it as a main amplifier. As you can see, the laser is shooting actually, because the laser is going to the first floor. So the laser is in the ground floor, but the laser is going to the first floor because the application is always in the first floor. So the beam is directed towards the first floor, and then they are now using for some laser shock cleaning, like hardening material, some material processing. So basically, by your naked eye, you cannot see, but your mobile phone is sensitive for this infrared radiation because this is around 1000 nanometer. So the 1000 nanometer, your eyes cannot see, but your mobile can still detect. It's like your mobile is detecting your TV remote camera, TV remote. So this is exactly the same like this. And then they also have a new world record that they send the 1030 nanometer, and this one converts into green color laser. So they have a world record for 1000 nanometer, two records, one is 100 joule. So this is like the system, the whole system. So this is huge. This is like 50 meters long. So one of the main component is the cooling, because when you talk about very high energy, you generate an extremely high heat. So this can damage the material, and this can be completely avoided by cooling. So the liquid helium plant is this one. So this is the one that's supplying the cooling source for the system for both the advanced materials. So they have a world record for 1030 nanometer, which is 100 joule and 146 joule. And then they convert it to the red color laser. And then for the red also, they have two records. So in total, there are 4 world records in our institute. Just to have an idea how the red laser will look like, I'm just showing this video. So this is how it looks. Actually, when the laser is operated very high energy, nobody can stay inside the lab because it's extremely dangerous. So this one was recorded at very low energy. So this is how the green laser operates at this pulse. So you can see the pulse. So the sound will be like da-da-da-da-da, something like that. So it's quite interesting. So this is a fascinating achievement, actually. So I will just share my slides again. So can you see the slides now?
One moment. Yes, sir. They're coming up.
Okay, so let me talk about what is a laser, because some people may not be familiar. So if somebody is asking you what is a laser, this is the easy way to explain. So basically, it's an oscillator. An oscillator is something like the kids are swinging. So it's like a swing. So you put a laser, a photon, a light photon inside an oscillator, 2 mirrors. The mirror will reflect back and forth. So the photon will bounce back and forth. So this is a resonator. So this is in technical terms, in physical terms, they call it as a resonator. But in layman term, they call it as an oscillator, actually. So it's like a swing. But the problem is when you place a photon in the middle, the photon will, after some time, it will disappear. It doesn't mean that it's like a magic. No, this is like a loss. Either the mirror will absorb or scatter or reflect, whatever it happens. So eventually the photon will lose. So this is what happens to your light. So what you need is you need an amplifier. So in a laser, you put a gain media. So
Sir, sorry to interrupt again. Your slide is still at number 11. Is it right?
Sorry?
Your slide is at slide number 11, right? You're still
No.
at slide 11. Yeah. Yes. Right now we're at slide 13, right?
Yes, I am at 13.
Yes, now it's visible, sir. Yeah.
So this is like the amplifier. So you have a gain media. So this is making an amplification. So rather, if you keep your photon just ideal between a mirror, it will die. So if you want to amplify, you need something that can amplify the photon. So this amplifier is called the gain medium. So this gain medium is the one that makes a big difference when you want to achieve a very high power laser. So this is one of the integral part of a laser system. So this is called the amplifying media or the gain media, solid state gain media or something like that. They have various names for this one. So I'm talking about a pulse laser. You see my next slide?
Sir, there's this common issue with Google Meet. Slideshows generally are not working. We ask you not to use a slideshow and scroll
Okay.
through the slides.
Okay, now you
We've
see
been
the
having
slides.
this issue since the morning. Yeah, now it's fine. We are at slide 14, right?
Yes.
Yes.
Okay. Okay, anyway, I had some animations anyway. So we have two types of lasers. One is like continuous wave lasers and the other one is a pulse laser. So we always talk about continuous wave lasers. So it's not like the laser pointer that you have like a keychain laser or like helium neon laser in your laboratory. All these things are continuous wave lasers. So easy to understand, like this is like a river. So these are not very powerful. Of course, these are powerful, but not very powerful. So if you save the same water in a dam and then you release it, so you close the door and then you open it, then you close it, then you open it, then it's like a dam. Then this dam is powerful. So this is exactly what is the difference between a continuous wave laser and a pulse laser. So in continuous wave laser, there is only one parameter. That is what they call like power. But in pulse laser, there are multiple things. You have like an average power. This is one of the records that I was talking about. Then you have like a pulse energy. Then you have like a repetition rate. This is like how many number of pulses per second. Then you have like pulse width. So how quickly you open and close the door. Like if you release your dam, how quickly you close the dam and then you open it. That's called the pulse width. And the pulse energy is how much water you dump. One time you open and then you dump the water. So you can imagine in a laser, in nanosecond time, you open and close. And in nanosecond period of time, you're dumping so much energy. There is like 100 joule or 145 joule. This is like a huge energy. And you repeat this like 10 times or 100 times in a second or like in an hour. That is called an average power. And this is like in 1 second, how many times you open, that is what you call like a frequency. Okay, I'm going to 15th slide, just to be sure.
Yes.
Okay, so the CW laser, so this is what you call the CW. So the power is constant. So you have a constant power. But in pulse laser, you're taking the, so this is why I'm comparing with the water. So you can easily understand using the water example. So you're taking the same water, then you store in the dam, then you release the dam. So in this case, you can achieve a very high energy. So they have a different parameter. So this is like the pulse energy, the maximum energy. So this is what I was talking about, like 146 joule. And this is like the pulse wave, how quickly you open and close, and then how frequently you open and close. So that is the repetition rate. And these are the important things that is very crucial to achieve the record laser. So if you want to build a very high energy laser, there are three, any laser, if you want to build, these are three main things that are critical. One is the pump laser, one is the gain media, and one is the cooling. Because the high energy laser, the cooling is one of the important parameters. That is why I was talking, I even showed in the video, there is a liquid helium. You can know the liquid helium temperature at 4 degrees Kelvin. So it's 4 Kelvin. So it's like minus 265 degrees Celsius. So this is extremely cold temperature. That is why it's very critical. So the first one is the pump source. So what are the choices we have? So what are the choices we have and why we have to select the particular pump source for high energy laser? So in a typical laser system, we have various pump sources. One is the electrical pumping, and the other one is optical pumping. A lot of people are aware they have like the laser pointer, like in a presentation or in some keychain. All these things are electrical pumps. So why? Because it has a battery. So all you have is like a battery. If the battery loses power, then your laser will die. And this battery is connected to a small driver, and this driver is emitting the red laser. So this is like the electrical pumping. So this is supplied, even your helium neon laser can be an electrical pumping laser because you connect with electricity. And so this is like a common pumping for a compact laser. Then you have an optical pumping. Optical means it's a light. So optical pumping is the first laser demonstrator. So this is the first laser demonstrated by the ruby laser, Neyman. So historically, this is the first laser in the world, and he got a Nobel Prize. And this first laser was optically pumped. So the first laser in the world was pumped by a light. So you pump a light, you get a light. So this is like an optical pump laser. And so he used the flash lamp. So it's a very nice story. If you have a chance, you can read about this story. It's a very interesting achievement, actually. So in optical pumping, you have two varieties, like Mayman use. Mayman use a flash lamp. So this is like a spiral flash lamp. It's like a spiral types. And the flash lamps is also like straight flash lamp. It's like a tube light. Okay, like a flash lamp that you put it in a stage in some shows. So these flash lamps are very powerful. These also can be used for like a pump source. So this is one of the pump sources that was used in the National Ignition Facility in the US to achieve this very high energy in megajoule. This is still in use. I'm not saying, okay, just get rid of all the flash lamps. And the other variety is the diode pump. So the diode pump, the diodes are very compact. So this is the advantage. You can make a system very compact and it's very efficient. All kinds of advantages it has over flash lamps. And some of the laser pointers that you have, the green color laser pointer, these are all the components inside the green laser. So you have a battery, and then the battery drives one laser, and this laser is a diode laser. And then this diode laser, that is why it's called DPSS. DPSS is diode pump solid state laser, actually. So the diode laser pumps another crystal. So this laser produces a green laser. So a light, so electrical is converted into light, and then light is converted into another light. So this is like a, from here to here is electrical pumping, and from here to here is optical pumping. So this optical pumping is one of the very crucial parameter for this kind of high energy lasers. So these lasers have advantages over flash lamps because they are compact and very simple. You see, this is the size of a coin, and very high efficiency, electrical efficiency. You can think about our flash lamps. These are very, very low efficient material. That is why if you stand next to a flash lamp, these are very hot. Why? Because a lot of your energy is delivered as heat, and it also has a longer lifetime and more stable. This generates less heat. That is why your white LED is not very heat generating, whereas your flash lamp it has a very high heat. So that's the big difference between diodes and flash lamps. So in diodes, we have various types. There is like a single emitter. This is like a low power. Then you connect multiple emitters. So you have 1, 2, 3, 4. So you connect multiple emitters, then it becomes like a diode bar. Then you connect multiple bar, 1 bar, 2 bar, 3 bar, 4 bar, then you become a diode stack. So you start from some milliwatt. This can be milliwatt. This is what maybe in your keychain. Then you go to some watt level, like 100 watt. Then you go to kilowatt. If you want to go to some kilowatt, then it's a stack. So we are here in our lab. We are using this kilowatt laser stack. We can generate like 280 kilowatt peak power, and the energy is to 650 joules. So you can imagine using a 650 joule power, they got something like 146 joules. So this is pretty good efficiency. So you're giving a light of 650 joule, you're generating a light of 146 joules. So you're giving some light of 940 nanometer, then you generate a laser of 1000 nanometer actually. And then the next part is the laser gain media. So this is where the advanced material comes. So in a laser media, you have multiple choices. You have a choice of a single crystal. A lot of people are working with crystals, and you have a choice of glasses, and you have a choice of transparent ceramic. And this transparent ceramic is the one that is used in our lab for this world record laser. But single crystals are still common, and the glasses are also common. So the single crystals, people are aware that they are grown by multiple techniques. One is like a Chakrovsky technique, and so you have very nice crystal, and you have a high temperature, very high temperature crystals are also can be grown like sapphire. These are like almost close to 2000 degrees Celsius. Some of the advantage of single crystal cells, these have high thermal conductivity. That means you can handle very high power, because one of the important parameter for a laser material is it should leave the heat. Okay, you're giving heat when you pump, so it cannot keep the heat with itself. So it has to give out the heat. That means it should have a high thermal conductivity. Otherwise, the system will crack. So that is one of the reasons people still prefer crystals. And there are hundreds of materials. But one of the drawbacks, the limitation is they are very slow. The people working with crystals, they know it takes even months. Some of the crystal even takes months to grow, and the dimensions are limited. Like even if you grow like 100 centimeter long crystal, you cannot use all the 100 centimeter. You have to cut, polish, and then you can use maximum like 40 centimeter or 50 centimeter crystal. So basically, you are growing a crystal very struggling, and then you grow 100 centimeter, but you're losing 50 centimeters. So this is like the low throughput, they call it. So you're losing half of the crystal. So this is one of the drawback of the single crystal. Then the other advantage we have is the laser glasses. The one of the laser I was talking about in the US, like the largest Livermore laser, they're using glasses because they need a huge gain media, which is not possible with crystals. That is why they're using glasses. So the glasses, they can grow in large volumes and sizes. Some of the glasses they used in the Livermore laser is in meters. So these are huge. So these are phosphate glasses, and also they have advantage. They have like broad absorption and emission band. That means you can have a very short laser pulses. The femtosecond, picosecond, they call these kind of short laser pulses can be generated by laser glasses. So once you have a short laser pulsar, you can have a very high peak power. So as you remember, which I was discussing about what is meant by a peak power in a pulse laser. So these kind of things is possible with glasses. But the drawback is poor thermal conductivity. People working with glasses, they know if you put your glass on your stove, the glass will crack. Why? Because it cannot immediately release all the heat. So it has a very poor thermal conductivity. That is why these glasses used in the National Ignition Facility. So this National Ignition Facility was attempted to produce some fusion reaction. And this laser, the problem was they have only few shots per day. So this is one of the problems. If you want to maintain a fusion reaction, you have to contain for a longer time. That is not possible with the laser. Why it's not possible? Because they're using glasses, and the glasses have very low thermal conductivity. Otherwise, the glasses will like shatter into pieces. Actually, this will be cracked. So now we have problem actually. We see the single crystals are advantages, but it limited by sizes. But glasses, they have multiple dimensions. They have like huge volumes, but they are limited by performance. So you want to have some combination. You want to have some cocktail of these good properties. You need to have some material which has a good thermal conductivity, and you should have also a larger size. And this is where the transparent ceramics is coming. Because here, this is a crystalline media, this is an amorphous media. So you have problem with crystalline media, you have problem with amorphous media. So you have a new option. This is like a polycrystalline media, that is a transparent ceramic. So the transparent ceramics, it has advantages of crystals. This is like large size and volumes, and they have like broad absorption and emission band. I'm sorry, this is not right. So they have like I think I missed the slides. Come on, I'm sorry. So we all know the ceramics is always the ceramic cup or ceramic toilet or ceramic plate, ceramic bowl. So all these ceramics are not transparent. So if it's not transparent, how can we make lasers actually? So one of the reasons that these are not transparent, or these are all have some impurities, some pores, these have some holes in it. So if the light is entering inside, the light is just scattered back or it's absorbed. So it doesn't come out of this ceramic media. That is why you don't see it transparent. So if you want to make it transparent, you need to make it. You need to remove all these pores and the impurities inside it. So these are the basic preparation of transparent ceramics. So it's exactly the same like how you ceramic, how you make a pot. So you take a powder. This powder is crucial. This can be nanopowders. Then you make it as a body, green body. The green body doesn't mean it's green in color. This is like a green vegetable. So this is uncooked body. That's why it's called green body. And then you process at very high temperature. Then you remove all the gaps. So all you have to do is here you have more gaps. Then you reduce the gaps. Then still there are some pores and impurities. If you remove everything, then you become transparent. Okay, so this is extremely simple. So it looks like simple, right? So, but they have some limitation. It's only limited to cubic material. There is a problem if you go for non-cubic material, you cannot orient in different direction. But it has a good advantage. It has a good thermal conductivity like crystals. And it also has it can be grown like in a larger size, like this size, like a glass. So it has both the advantages. And also like spectroscopically, it has some advantages. It has a very good spectroscopic properties and also laser properties. So this is why the transparent ceramic was chosen for this kind of application. So there are two main ways that you can generate powders or the transparent ceramics. Both these inventions were made in Japan, actually. So this was not easy. It took almost 15 years for them to prove. So because the process looks simple, right? So you take a powder, then you press the powder, then you heat the powder, then you make it, then you get a transparent ceramic. It doesn't look very straightforward. Like Japanese are very hardworking. Even for Japanese, it took 15 years. And so these are the main two techniques they use. One is called the solid-state reactive sintering, and one is called the co-precipitation. So the solid-state reactive sintering is the first. Any problem? Any problem with the slides?
No, sir. No, it's fine.
Okay. Okay. So this one was achieved in 1995, just 25 years back. So this one was achieved by this guy, Ikesue. Actually, I had a chance to talk with him once. He's a very nice person. So all he did was he just mixed powders. So it's like you take A, you take B, and then you mix the powder into AB. So in this case, he was making yttrium oxide and aluminum oxide, and as a dopant, he was using neodymium oxide. So you mix the powders, and then you mix it, then you press it, then you press again, then you heat it, then you polish it, then you get a ceramic. But the problem is, so it's very easy, right? Like you just take powders and then you start mixing it. It's easy to scale up. You can mix kilogram of powder and then it's faster. You can make it quicker. But the problem is it's not of very high quality. There is a problem because when you mix this, you always add some extra impurities because you're mixing with some balls and stuff. So this is like the ball milling and stuff. So these balls add impurities. So this is why it's limited with some purity. That's why he was the first one to make this transparent ceramic, but he was not successful commercially as a transparent ceramic guy. That is when these guys, the same Japan, but this is from a different company, which is very famous, Konoshima Chemicals. I also had a privilege to work with them. I even have a paper with them actually. So these guys came up with a new solution. So if you mix A and B like a solid material, the mixing is not uniform. It's like you take an onion, you take a tomato while cooking, and you are mixing it. Of course, you can mix it as much as possible, but it's not very uniform. So the easy way to mix is, you crush the tomatoes, you crush the onion, then you mix it. So you make as a solution. Then you make another solution, A as a solution, B as a solution, then you mix the solution, then it becomes well mixed. So that is why Ikesue took as a powder. So he took as a powder. So what Yagi and Yanagitani, so these two guys took as a solution. So they dissolve it and then they mix dropwise. So here they achieved very high results. And the ceramic, what we use in our lab, in our institutes, is from Japan. It's very expensive. It's in crores. I'm talking about like crores of ceramic. Just imagine you make one slab and it's like a crore rupee. So this is why they have a good control, very high quality, and this is suitable for high power laser. One of the problem is this is very time consuming because you have to add like drop by drop. But just imagine like with Ikesue, it's like you take 1 kilogram, you mix for a few hours. It's very straightforward, but not Konoshima. It's like you have to add drop by drop. So this is very time consuming. That's why it's very limited. Even now, Konoshima is like a monopoly. So if you want to get a good ceramic, you have to go to Konoshima. Otherwise, your laser will not be very efficient. You can get a lasing. Of course, there are many groups in various parts of the world. But if you want to get a very high power laser, the only company that can do is Konoshima. Even a lot of Americans are not happy with Konoshima because of that actually. So once you have the powders, then you go for the pressing. So you shape it. What kind of shape you want? Either you want like a cylindrical shape or a spire shape. And so this is, they call it the forming. So then you give a pressure. So this is like a low pressure. So you take a powder, then you press it. So then you achieve like the density of 20 to 30%. So I'm talking about a very low pressure. So this is like 30 to 40 megapascal. But the problem is your pressing has to be very precise. It's easy to crack. So this is very simple, but also very complicated sometimes because you had to do several times. So this is the first step, which is very important. Then you increase the pressure. So here it is 40 megapascal. This is like 30% density. Then you increase the pressure to 150 to 200 megapascal. So here the pressure is in one direction. So this is called the uniaxial pressing. The pressing is from only the top direction. And in this case, the pressure is from all the directions. So this is like the isostatic pressure. So this gives a pressure from all the directions, and the pressure is extremely high. This is like 150 to 200 pascals. So this is like the 5 times the pressure from the previous one. And now I'm increasing the density to 50 to 65%. So I'm increasing the density a little bit higher. But again, there is a possibility if your pressure is not good, then you will have a crack. and then you go for the heating. So you still have a long way to go, because all you need is almost 100% density. Any kind of like lower than 100%, 99.9% is acceptable, but 99.5% is not acceptable. So you need to have a very high density. So you cannot do with pressure alone. Then what you do is you deal with temperature, because temperature produces pressure. And so that is why they go with temperature. So you apply a temperature of 1700 degrees Celsius. Then you grow the grains inside. So the grains grow and remove all the gaps. So in this way, you can achieve very high density. So this is what is happening. So before, when you have the powder, then you have this one. When you apply the pressure, you still have some hole in the middle. Then you put the temperature, and the temperature will just disappear. And when you have it, then you have it transparent. So it's very simple, straightforward. So this is the various mechanisms that is involved: diffusion, all the grain boundary diffusion, surface diffusion. I even have a chapter on it. I can send you if you want, actually, to have a clear understanding of this. So what are the biggest challenges? Why everybody? So if this is very simple, why not everyone is able to make it? Is because the controlling the powders, controlling the pores, and everything is crucial. So if you have a powder in the if you have a pore in the boundary, then it's easy to close it. But if you have a pore in the center, it's very, very difficult. And this is like, that's it. If you have some few pores in the center, that's your ceramic is useless for high power lasers. So one of the reasons is when you have a smaller size, you have to give a very high pressure. And that high pressure, even with temperature, is not possible. So you have a smaller pore size and the higher driving force. But there is another way that you can solve it. So there is another process called hot isostatic pressing. So as we mentioned, so you have to go all the way to this 100% density. For example, if you look at the grains, you still have some pores. So in these kind of pores are not useful, actually. So this has to be removed at 100% theoretical limit. That is why it's recommended to use a vacuum centric. Why? Because sometimes when you heat the temperature, some of the gas molecules will go and get trapped, and these gas molecules will form as a pore, and this gas is very difficult to remove. This is not like a balloon. Okay, so this is not easy to remove. So you have like gas traps. That is why people work with vacuum sintering, and vacuum sintering is very expensive. That's why people are very limited. So this vacuum sintering is avoiding any kind of gas traps, and this will have an opportunity to avoid these kind of pores in the center of the grains. And there is another way that you can, after the sintering is still, your ceramic is not good, then they go for the other process that is called hot isostatic pressing. So this is a very interesting, very expensive process in which you apply both pressure and temperature. So first we start with low pressure, then we start with high pressure, then we start with high temperature. And here we are talking about high pressure and high temperature. And here the high pressure and high temperature, all these things are applied in all the directions. This is why it's called isostatic pressing. In this case, you can achieve pretty high, good transparent ceramics. So some of the parameters are very crucial. Some of the parameters people take for granted. Oh, this is not very crucial. We can just play with this, adjust that. But every parameter is very crucial in transparent ceramics. Just for an example. So this is like a ball mill alumina. So you can see that you are using a ball of alumina, and you have one property, and you have ball mill with zirconia, then you have another property. You have the same powders, but you just ultrasonic, and then you do it, then you have another property. So this is why you had to do trial and error. In material science, it's not like theory that you just, okay, you predict it, your computer says it, you just follow it. No, you just follow different procedure. You just change parameters. You just change the ultrasonic time. You change the ball milling time. You change the ball that you use, and everything is affecting the quality of the ceramics. Just imagine you have an effect of sintering temperature, how you heat, how much temperature you give. So I'm giving a temperature like 1790, then I'm giving a temperature 1800, just 10 degrees Celsius difference. And you can see the big difference. The quality is completely gone when just a 10-degree change in temperature. So this will affect the quality of the ceramic significantly. So that's why the temperature is also crucial, that you had to play with your temperature. And also even the heating rate, how fast you heat it. You heat at 2 degrees per minute, and you have one kind of structure, then you have 10 degrees per minute, you have the other shape, then you have like faster, then you have, so if you increase the heating rate, so you want to finish your experiment very quickly, but you will have problem. You will have more porosity means very poor quality. But even though the grain size is still the same. So, and the other quality, so the ceramic, what we use in our lab is the yak ceramic. So as I mentioned before, this is a combination of yttrium oxide and aluminum oxide. The problem is the yak itself is a problem. So it's a fundamental problem. So they call it as a lime compound. So this is like the garnet, the phase diagram. If I move a little bit outside, I'm outside the garnet. If I look below a little bit this side, I'm losing the garnet. So this is why it's very critical. Like YAG is like very common material, but even though it's common, it's still challenging. Because when you grow a crystal, your crystal melt will avoid all these kind of external phases. Your crystal will take only the garnet. But in the case of ceramic, it doesn't have any mechanism to remove it, to exclude it in a liquid. No, this is all in solid phase. So when you put it in the solid phase, this is why even any extra impurities, your phase will change. When you have an extra phase, then you will have extra impurities. The secondary phase will destroy the quality. So this is one of the crucial points. So you can just, so this YAG was invented very long time back, almost 40 years, 50 years back. But for the ceramic, it took a long time. Why? Because it requires very high purity powders. It requires a very narrow distribution of particle size. Every parameters, every processing condition, heat, temperature, heating rate, the ball milling time, the ball milling balls, and the ball milling ultrasonic time. All these things are parameters. That is why it took a long time. It took almost 15 years for the Japanese to achieve this high quality ceramics. So this is what we are using. So this is because it's very high thermal conductivity, and you can also have a cladding. You see, this is one ceramic, and this is another ceramic in the circle. Why we have this cap and these kind of things is, so in high energy lasers, we always have problems. So this is like the gain media. We have like a slab. You have a uniform slab. Then you pump with laser. So as I mentioned before, you pump with light, then you generate a light. So I'm pumping with diode. That is why it's called a diode laser pump. Diode is not like electrical pumping. Diode laser is a light, and this light is pumping on the sample. And when it is pumping, it generates a lot of heat. You see, when it generates a lot of heat, and here it's cold and here is hot, so this can damage it. So this is a problem. So this has a severe thermal issues. So what is the solution? What we can do? Then the scientists found out that if you have a lower dopant, if you have a concentration of the neodymium, then you have a high thermal conductivity. So they can play with this. So in the front phase, you want to avoid the heat because this is where the laser is falling. So how I can avoid it? So they came up with the indigenous idea that you can have a lower dopant. So as I mentioned before, when you have a lower dopant, then you have a higher thermal conductivity. When you have a higher thermal conductivity, it can remove the heat very quickly. So what they did is they first put undoped ceramic. So the laser is falling and no heat. Then the laser is going inside. Here the amplification takes place, and then the laser is going out. And you have another pump source from this direction. Then you have again no heat. Then the laser is amplified. Then it is going out. So it's a very, very beautiful design. So that's what they call gradient doping. So there are two ways that they can do. One is like you put one layer, then you put a dopant layer. So the amplification really happens here. The temperature, the heat happens here. The heat also happens from this direction. So the amplification happens only here at low temperature. So this is what is one of the things they call it a monolith. But there's also another type. This is called the slab laser, so multi-layer. So this is what they call dopant gradient. So they increase the dopant, or they call it clad core. This is like the clad, and this is like the core. And there is also the other mechanisms which is employed in our laser system. It's like a multi-layer. So you have like multiple slabs. So you start with low concentration, then you keep on increasing the concentration, and then you decrease the concentration. So you have a pump source from various directions. So in this way, you can avoid the heat. So because your pump is on the first phase, the first phase has low concentration, so high thermal conductivity, so the heat can be avoided. At the same time, the amplification can be done. So this is the system I showed in the video. So this is where we started. The video started here. So this is like a nanojoule, goes into millijoule. The millijoule becomes 100 joule. And then the beam goes all the way here. And here it converts into 10 joule. Then the 10 joule goes all the way here, and from here, the world record power of 100 joule. So the main amplifier, the main preamplifier I was talking about is 10 joule, and then the power amplifier is 100 joule. So in the main amplifier, we are using the 4 slabs of the ceramic. So as I mentioned before, the first slab is 1.5, a little bit lower, and the amplification happens at 2%. So this is what helped to achieve the 10 joule laser. This is like a circular shape. And then the main amplifier. So this is where the world record happened. So this is like a square shaped ceramics. And here also they have like two kinds of things. So so here there is two outer ceramic, which is lower concentration, 0.4 and 0.6, and this is 1%. So you can just think, oh, why there are so many concentration? One is like 2%, one is like 1.1%, one is like 0.6, one is like 1. This is based on simulation. So there are some laser simulation. You can find how much concentration you need to get some amplified power. So this one was the first world record. So this is the world record energy. First, we got like 100 joule at 10 hertz, just like 1 kilowatt average power. This is like at 1 second, they have like 10 pulses. This is like remarkable. So this is the laser. And then they achieved this 145 joule last year. As I mentioned, I'm not the part of the team. So in the video, you can see that I was with Peter actually. So Peter was showing the lab to me. So yeah, if you happen to visit Prague, maybe I can show you around the laser actually. So this is a very remarkable achievement. I don't think anyone can break this world record anytime soon. So this record will stay for a while because building this kind of laser is not so easy actually. So thanks to all the advanced materials, ILAS has now holds the 4 world record actually. So thank you very much for your participation. I apologize for all the technical glitches here and there. I hope it's useful. I did not talk too much technical. I just shared some fundamental how the materials actually play a major role to achieve the very high power lasers actually. So in India, we should invest too much and we should work towards this kind of materials. Unfortunately, in India, the number of labs working on these materials is very limited. I don't think any laser has the laser quality ceramics even produced in India. Thank you for the opportunity once again. Thank you.
Thank you, sir. I request the participants, if in case they have any questions, to please post it in the chat box. The speaker will answer them shortly. You can post your questions in the chat box. The participants are requested to post their questions in the chat.
Maybe the presentation is very clear.
No.
If there are no questions, I'm happy. So no problem.
I
will stay here.
Yes.
I can also share the slides. If you want, I can share the slides. I will share my, you can also note down my email ID. You can send me an email. I can send the slides. I'm not like the person who is hiding the slides or something like that. So you can send an email to me actually. I am posting my email ID in the chat box. So you can send an email. I can send the presentation. Yeah, you can ask the question.
Yes. My question basically revolves around the generation of lasers. We give a very high input in kilowatts, in fact, and we get only a laser of very less power. What happens to the residual power?
Yeah, that's really good question actually, because always people think, oh, if we already have a very high energy, why we have to generate low energy? The problem with the diode lasers is not very effective in industrial applications. Because you know, even though the diode is divergent, you can just take your red laser pointer. You just shoot on your board. From your hand to your board, already the beam is a little bit bigger. Just imagine if you're transporting some meters, this power will just diverge. That is why these kind of lasers, which we generate, it travels very collimated for a very long distance. And also the wavelength is different actually. And the question which you asked, what happens to the remaining power? Of course, it's heat. This is why we need liquid helium. We need liquid nitrogen. So that is why they're flowing like one, honestly speaking, every hour they spend so much money just for helium. That is why these lasers are very expensive. Yeah, what to do? Yeah, so this is a heat. Yeah, this is the heat. This is a short example.
We have a question from Nupur. Nupur wants to know when ceramic becomes transparent, what happens to its strength?
It's interesting with ceramic actually. In ceramic, you can play with the grain size because in a single crystal, it's like only one grain. Okay, in a single crystal, it's one grain. But in ceramic, you have multiple grains. If you reduce the grain size, you can change the mechanical strength. So in ceramic, the beauty is with smaller grains, you have a very high mechanical strength actually. So the ceramic actually it has a better strength than single crystals. Actually, that is the fact.
Participants, a reminder again, if you have any questions, please post it in the chat box.
whether we can use the heat energy released for any other purpose. Unfortunately, we cannot. Yeah, because these are like localized. So I'm having a ceramic. So this is my mobile. This is my ceramic. Okay. My heat is generated here. So what I'm doing is I am flowing my helium right here. So the helium is actually removing the heat right here actually. So if you put your helium here, no, this is not good. So that is why they're flowing helium like blowing actually. They're really pouring the gas of liquid helium very fast. And this heat is immediately removed. It cannot be extracted very easily.
We have another question from Karthik. Karthik wants to know if in case he has a material with 4 electron volts direct transition, will he be able to construct a diode laser theoretically? Is there any property he has to look for?
The difference between a LED and a laser diode is the mirrors. If you just take a red LED and put a mirror, it becomes like a diode, laser diode. So the only difference, so if you have a direct transition, if it's emitting, and you all you have to design is basically, I do not know what is 4 electron volt is in nanometers actually. 4 electron volt in nanometer, any idea? Yeah, if you ask in nanometers, because there are many diodes that is available. Yeah, I understand 4 electron volt is a band gap, but can you give the band gap in nanometer? This electron volt band gap can also be mentioned in nanometers actually. Yeah, so you can convert the electron volt into nanometer. If you can just tell me the nanometer, because there are many diodes, you can just tune the concentration of the semiconductor. You can generate various lasers. Okay, 300 nanometer. Yes, it's possible. Yeah, there are 300 nanometer laser diodes are available. All you have to do build is a mirror. Just imagine your semiconductor, you're talking about like micron size. You have to make a mirror of micron size. That's why it's challenging.
I think we have another question from Balasubramanian. Balasubramanian wants to know if is there any type of shutters in your world record experiment?
I don't understand what is meant by shutter, but they're using, they call it a beam dump. So the beam dump is if you don't use the laser, this is directly going to the dump, and this will just absorb the material. This is water cooled, so this is like, as you mentioned, like this is generating heat, so this can just protect this one actually.
Yeah. Participants, just once again, if you have any questions, please post them in the chat box. The speaker will answer them for you. If not, we can.
Otherwise, yeah, you can send me by email actually. Yeah, I think people are curious.
Yes. Sir.
Yeah.
Okay. The link for the feedback link for this session is currently up in the chat box. You can go ahead and fill them. And I profusely thank Dr. Samuel for this wonderful session. I'm sure the participants found your session very informative and fascinating, sir. Thank you once again. Thank you.
Yeah, I thank the management, the head of the department, and Dr. Kavita, and also, and I apologize for the technical glitch. Actually, I was not aware because I missed some of the slides. Thanks again. I hope it's useful. If you have some doubts, please feel free to shoot any email. Actually, I'll be happy to reply. Thanks.
Yes, definitely, sir. Thank you so much.
Thank you.
Thank you, everyone. Thank you, everyone, for joining. We are very delighted to see you all here today. And we have another exciting day coming up tomorrow. So for tomorrow, we have speakers from various places coming and joining us. Our notable speakers for tomorrow include Dr. Ramya from Illinois, United States, Dr. Bibin John from ISRO VSSC Thiruvananthapuram, Dr. Jayant Murthy from Indian Institute of Astrophysics, Bangalore, and Dr. Crispin Karthik from Indian Institute of Astrophysics, Bangalore. If in case you missed any of our today's session, you can go ahead and check them in our YouTube. We sent you the links via mail. Also note that the tomorrow's session begins at 9 a.m. IST, unlike 10 a.m. IST. With this, we sign off. We hope to see you all tomorrow, and thank you, everyone. The feedback link for this session is posted in the chat box. We request you to kindly fill it also. Thank you, everyone. Bye-bye.